Hello, good evening, Jayakumar sir. So we'll start at 6. We're just waiting for participants to join.
Sir,
Good evening, sir. Sir, am I audible?
Yeah, you are audible. Am I audible?
Yes, sir, you are also audible.
You have corrected that?
So we are on it. We just need 30 more seconds.
That's a big blunder.
Thank you, sir. We're so sorry about that.
I just noticed. ONAR Capital, Outreach Advisor OR Capital.
Okay, sir. So we are waiting for at least 50 participants to join to begin. We'll just wait for 5-10 minutes and then we'll start.
Sure.
Thank you, sir.
You are a faculty or student there?
So student.
Yep.
So I'm pursuing ACM here, Advanced Construction Management.
Post graduation or
Post graduation, yes, sir. PGDM.
yeah. Yep.
Hello, good evening, everyone. Uh,
It's not audible.
Hi, sir. I was asking, shall we begin the session now? Sir, your mic is off.
Yeah. If you are ready, I am also ready.
Yes, sir. So, good evening, everyone. Welcome back to our day 4 of the AICTC Training and Learning Atal Academy sponsored FTP on digital construction and green design, pathways to net zero. We, the Innovation Cell, NICMAR Delhi-NCR, appreciate your continued commitment as we move into the final phase of our program. Today, day 4, we will synthesize these learnings by focusing on two critical areas: water resources, a fundamental element of green design, and digital monitoring, the technology that ensures structural health. We expect today's session to be just as enlightening and insightful. Today, this session topic is sustainable urban water and waste management. Sustainable water use and efficient waste management are cornerstones of green building, directly impacting energy consumption and environmental integrity. With this, it is my immense privilege to introduce a distinguished academic, policy advisor, and expert in water resources, Professor K.V. Jayakumar. Welcome, sir. Professor Jayakumar is currently serving as a visiting professor cum outreach advisor at the Indian Institute of Technology, Dharwad. His expertise spans 32 years and provides a comprehensive view. He has previously a professor of civil engineering at NIT Warangal since 1993, holding significant role including dean, planning and development, and head of department. His expertise encompasses hydrology and water resources, urban stormwater management, and environmental management. He has served as the executive director of the Center of Water Resources Development and Management and is a governing body member of Wetlands International South Asia. He is an internationally recognized expert, having held visiting assignments in Germany and Australia and coordinated international course on urban drainage in developing countries. We eagerly anticipate his guidance on integrating crucial water management strategies in our net zero pathways. I now invite Professor K.V. Jayakumar sir to take the stage for the session.
Thank you, Kanyakumari. Let me share my presentation.
Yes, sir.
Is the presentation visible?
Yes, sir, your presentation is visible.
Yeah. Okay. So the next an hour and a half almost, I'll be talking on the various sustainable urban water and waste management, focusing towards the modern areas. This area, I've been working on these areas for many years, and I'll just try to cover many aspects in the short time that I have here. Now we just look at the water on Earth. What is available is the total water on Earth, and what is you see a dot here is a liquid fresh water, and there's a small dot here. There's fresh water available in lakes and rivers. So you can just see how much water is available on Earth, and we are trying to manage. Now, if you look at the whole world, this was prepared in the year 1999, when we entered the new millennium, to find out how much water is available in the world. So look at 1950, just after we got independence. In this map, the dark color shows very low amount of water. The light color shows there is no shortage. So look at this map of India. In the year 1950, we were in the lighter color. 1995, the color became darker because we started developing, the population got increased. We increased our agriculture, we start urbanizing, industrializing, and the same trend continues. This year, this was the predicted water availability in the world. That means it's dark color. Water availability in the sense, it is 1,000 cubic meter per head per year. If the amount of water is less than 1,000 cubic meter per head per year, we say it is catastrophically low amount of water. So this map was prepared in the year 1999, before we entered the millennium, to understand where we stand across the world. Now, this map was not accepted by many people. So this was corrected in the year 2005 by the International Water Management Institute. Now, look at this map. This map shows, let me consider India. You find here the center portion of India is in red color. Red color means physically water is not available. There is physical water scarcity. And on the coastal areas of India, starting from West Bengal, Orissa, Andhra, Kerala coast, and Karnataka coast, Goa, and then Maharashtra and Gujarat, there is going to be economic water scarcity. Economic water scarcity means what available, but no money to develop. And you look at this, the whole of South America is the same condition. The whole of Africa is in this color. Whole of Australia in this color. And China is there. But the blue color says there is no shortage of water. The whole of North America, the whole of Russia, major part of Europe did not face any water problem as projected by this. Now, this map again was not accepted by many countries. It was revised in the year 2013. Now, this shows there's a scale. You can see a scale here. This scale shows the amount of water available in cubic meters per head per year. So this is the map prepared in 2013, about 12 years back, which is now accepted across the world for water management. And water is an important sacred source. So if you look at this map, you find whole of America. There you see this color here, this blue onwards, it is no shortage at all. And the dark red color that is here, that area is absolute water scarcity. The red color says it is the scarcity, and the yellow and light orange color shows there is stress and vulnerable. So look at India. India is under water stress vulnerable. So that is what is accepted, and that is what is today's condition. So, and you find the whole of America is no problem. Major part of Russia, no problem. China has similar problem like us. Australia has no problem. Philippines, Manila, etc. no problem. And major part of Africa doesn't have any problem, except the northern part where there is shortage of, there is going to be absolute scarcity. So this is the map prepared for the whole world now, which is now being accepted as the total renewable water resource per capita available. So this scale that you have here shows the amount of water per capita in cubic meters per head per year. So India is in this condition, that is, India is a water stress and water vulnerable country. So now let us look at the definition of sustainability. That's what we were talking about. Sustainability perhaps has a very aptly been defined by the World Commission on Environment and Development, which is called WCED, in the year 1987. This definition was given by Madam Brundtland, who was then the Prime Minister of Norway. It says, meeting the needs of the present without compromising the ability of the future generation to meet their own needs. A definition which is accepted across the world. Now, there are 5 kinds of sustainability development that we talk about. One is technical. Technical means the effective and efficient design and management of resource development projects involving balancing variable and demand and supply. That means our demand supply should be balanced. Technically, they must be very sound. The second sustainable concept is on environment. There can be no long-term irreversible effects. So any development that we do has an impact on the environment. So if you're going to a sustainable development, that means there shall not be any long-term irreversible effects on the environment. Then there should be financial sustainability. Whatever money we spend must be recoverable. So cost of all resource development and projects must be recoverable. Then the social sustainability is society must support and be willing to pay for services provided by the development projects. Then whatever project government is taking up, so we should support and be willing to pay. That is something very important. Ultimately, an institutional sustainability where the institutions which have the capacity to plan, manage, monitor, and adapt to changing situations. So you have 5 important conditions for sustainability: technical, environmental, financial, social, and institutional. Now, the main challenges to achieve water security is that the basic needs must be met. That water is a basic need. There should water for food supply, and the water supply should be reliable. That means many times what happens in urban areas, we see in our country also, the raw sewage overflows into open drains because sewers are blocked or pumping stations are not functioning. In rural areas, hand pumps can remain out of order for months, while latrines too often are used for purposes other than for which they are designed. Then they must be financially sustainable, environmentally sustainable. So most cities, what happens now is the agriculture is competing with the water rights, and very few contribute to pollution abatement. There is weak water body. Villages rely on groundwater, suffer from rapid depletion of aquifers, whose mining for irrigation purpose is encouraged by highly subsidized power rates. So power rates are highly subsidized. The charges that we charge for water are very, very low compared to international standards. And so it becomes very difficult to provide good quality services. So most of the time, the poor people suffer because the services are very poor. So the challenge today in water sector is not to increase access to infrastructure to everybody, to almost 100% population, but to increase access to reliable, sustainable, and affordable service. So we in India, we are unlikely to be able to meet this objective unless we adjust our policies, our institutional arrangements, the financial incentives to help improve the service delivery. So what happens when you urbanize, the water crisis automatically comes. So the global water scarcity will be felt in the arid, semi-arid areas. Arid, semi-arid means a place where you get less rainfall, and also the rapidly growing coastal regions. So we find that many of the cities already are or will be unable to provide safe, clean water and adequate sanitation facility for the citizens. So these are two fundamental requirements. The providing safe water and sanitation are the two fundamental requirements. So we find the problem is getting magnified by rapid urban growth. In 1950, there were less than 100 cities with a population next to 1 million, but today that number is expected to rise around 650. So 100 cities, the 1 million, 10 lakhs. This is across the world. Today we have got 650 cities, we got population of more than 10 lakhs. So in 2000, there were 23 cities, and 18 of those 23 cities were in developing world, had population exceeding 10 million. 10 million means 1 crore. On a global scale, half of the world's people live in urban areas. So some of the world's largest cities depend heavily on groundwater and for the water supply, but it's unlikely that dependent on the aquifers, which may take many years to recharge, will be sustainable. Already water shortages are occurring in many parts. So you find that we urbanize very fast. India is the second largest urban system next to China. It is urbanizing very fast. Now just look at this map. Now this is a urban scenario. Shows what is the percentage of urban people in the urban areas, starting from, let's say, 1991, projected up to 2030. So in 1991, we had about 26% of our population living in urban area. In 2001, that 2% increased, and in 2030, 40% of the people are going to live in urban areas. That means this source is a very beautiful book written by the McKinsey Global Institute, and it's a very beautiful literature that we have. And if by 2030, 590 million people are going to live in the urban areas in India. So there's going to be a lot of problem then. So you find as the population grows, water use will need to shift from agriculture to municipal and industrial uses. So making decision between allocating water between agriculture and municipal industries is going to become very difficult. So just to have an idea, when we got independent, we got 2,800 municipalities, and today we have 5,500 municipalities. 7 cities, class 1 cities, a population of 1 lakh. Today we have 600 cities, which have got more than 1 lakh population. 5 metros at that time, metros were considered 20 lakhs plus. Today we have got 60 cities having 20 lakh plus population. So that means we are mainly an urban city going towards urban area. So what is happening in urban area? Most of the economy takes place in urban area, and 60% of the economy comes from the urban areas, and the urban areas become hubs for enterprise, innovation, people and politics, and most of the economic growth depend on the productivity of the urban areas. So just to give a comparison, what happened, the contribution to GDP from the urban areas in 1980-81, 47% of the GDP came from urban areas, 1991, 55%, 2000, 2001, 60%, 21, 73%. So today it's around 78% of the GDP is contributed to urban areas. So obviously urban areas need a lot of importance in a country like India. So what is happening in a country like India is we have what we call a low-level equilibrium tap. So the amount of money invested in the water sector is very low. When the water sector is very low, the level of services provided also be very low. So when you provide low level of services, people are not ready to pay. Then the low level of willingness to pay, when people are not ready to pay, poor cost recovery, and when the cost recovery is very poor, the level of investment decreases. So you find that we are going to get into this low-level equilibrium trap. Now, in the past 25 years, this has changed. This has changed to the better one. So today we have higher level of investment in the water sector. When this level of investment high, we get better and improved level of services. When the services are good, people are, the willingness to pay is very high, and the government is also ready to charge more money. And once the willingness to pay is high, you find a higher improved resource mobilization. And once the mobilization is good, then investment can be done. So you find that this is what is going to happen. That means from this lower level equilibrium trap, we have to change to a virtuous circle, and that is what is happening now in India. So there is a lot of investment in the water sector. Now quickly let us go through the Sustainable Development Goals. Now this was on September 15, 2015. Countries adopted a set of goals to end poverty, protect the planet, and ensure prosperity as all. And this was called as the Sustainable Development Agenda. So each of these goals, which are there, goals are to end poverty, to protect the planet, and ensure prosperity. So these have to be completed by in the next 15 years. That means 2015 means by 2030 we should end poverty, protect the planet, and ensure prosperity for all. So for this goals to be reached, everyone have to do their part. The government, the private sector, the civil society, and people like you and me. So that is what is going to happen. Now quickly, let us see what is happening. So when we entered the new millennium, we had, this is the year 2001, we had set up 8 goals, 8 out of which the goal number 7 is for ensure environmental sustainability. So this was basically prepared the year 2001, and to see that by 2015, all these are met. That will eradicate extreme poverty and hunger, everybody gets education, empower women, reduce child mortality, maternal health, and control diseases, and develop a global partnership. So this was basically started in the year 2001. And 2015, we have shifted to the Sustainable Urban Goals. Now, just to compare these two, You find in Millennium Development Goals, the 8 goals and 21 targets, deadline was 2015, and it was relevant to developing countries, not the highly developed countries. Then when many of these were not met, because by 2015, many of these were not met, they shifted to Sustainable Development Goals. And Sustainable Development Goals, there is separate goal for water and sanitation, and then they're relevant to all the countries. There's 17 goals, 169 targets, and by 2030, this must be there, must be sustainable for the whole world, relevant to all the countries. You can just see the difference here. It's relevant to developing countries, relevant to all the countries. So this is from the UNDP report that I've taken. So quickly, the Sustainable Development Goals, we got no poverty, zero hunger, good health and well-being, good quality education, gender equality, clean water and sanitation, then affordable and clean energy, then decent work and economic growth, and then industry, innovation, infrastructure, reduced inequalities, sustainable cities and communities, responsible consumption and production, climate action, life below water, life on the land, peace, justice, and strong institutions, and partnership for goals. So these are 17 goals which are enunciated in the year 2015 to be met by year 2030. So if you look at the Sustainable Development Goals, there's a separate goal for water and sanitation. So you find everybody should get water, universal water, universal sanitation, water quality must be good, efficiently supplied, integrated management, and natural ecosystem. You find that's a cycle that we have. This is what we call the Sustainable Development Goal in 6. Now, this was the situation in India maybe 25 years back when we were not having enough water. Water is sent by trucks. Even today, it happens in many parts of the city. People rush for collect water. They walk miles together to collect water. This is a picture taken in Rajasthan area. We were even supplied water by train from surplus area to deficit area. The whole train had maybe 125 tankers like this carrying water. So this was the year 2000, and a lot of water bodies were developed. This is a picture of the cyclone of Orissa, where part of the Orissa was submerged. And because of improper development, you find cities are flooded, which again is happening now. And this is a part of the city of Hyderabad, which is flooded today, is not there. And now, how did we solve in the past? In the past, we had constructed many religious places. The temple tanks were basically the rainwater harvest structure, and the center portion you have this, and this basically is focusing on clean water. People come, take bath here, go here, collect water, and take it to their house. You find some of the tank in the olden days where having all the rainwater temple tanks were part of the rainwater harvest structure in the past. Now, just to see how a city has planned the water resources, this is a city of Hyderabad, one of the good example in the country. In 1991, the city had a population of 3.3 million, and the water requirement was 722 million liters per day, and they had only 545 million liters available. That means there is a shortage. So the government started trying to identify more sources. In 3 years, the population increased to 4.35 million. The water requirement increased to 9.913 million liters per day, and they could identify at 135 million liters source. Then 2001, a lot of sources were identified. The neighboring catchments were identified, and you find a population 6.23. The water requirement is 1105 milliliters per day, and they could get 1090 milliliters. That means there is slight shortage. Then more area of water is covered. In 2011, you find the 8.19 million population, and 1862 is the amount of water required in milliliters per day, and they had collected enough water of 1906. That means in 2011, the city had more water than what is the demand. So this should have been continued. Unfortunately, they did not do much development. When 2021, what happened? you find the population increase to maybe cost more than 1 crore, and the available water, the required water increase like anything, and this 1906 total amount of water that can be taken the maximum, and you find there's a shortage. So there the government did something to increase the source, but then because of unplanned development, the water supply is not necessary, not meeting the demand. So this is a good example of what a city could do. Now, in some part of the country, even today it's available in northeast part of the country, where they use the bamboos for taking water, very cost effective. Its bamboos are hollow, the water are taken all over the place. They are shaped stubs, and water flows with gravity. Some place they open up to the water gets purified, and that's how it has been going. So we find that some examples I gave from different part of the country, and we find that good cities are necessary for sustaining economic growth. High quality municipal infrastructure services are essential for enhancing urban productivity, especially for the poor. Now, the government of India will set up certain benchmarks for water supply. You find water supply should be covered 100% of people should get water supply at what rate? 135 liters per capita per day, and the water should be metered 100%. There could be 15% non-revenue water. Non-revenue water means water from which you don't get any revenue. And the water supply should be 24/7. That water supply should be all around the clock. And if there are any complaints, must be addressed, 80% complaint must be addressed. And there must be treatment for 100% of water. Cost recovery must be 100%. And efficiency in collecting water-related charges is 90%. And no one should receive less than 70 liters per capita per day. So that is for the water supply. Then you have benchmark for sewage. Sewage 100% must be covered. Collection of wastewater network 100%. Wastewater treatment 100%. Quality wastewater treatment 100%. Reuse recycling at least 20%. Cost recovery 100%. Consumer complaint redressal 80%. Collection charges 90%. House connection 100%. Coverage toilet 100%. You see, this is the benchmark we set up for all of us. And solid waste management, you also find that all the household level service must be 100%. Collection of municipal solid waste be 100%. Segregation of municipal solid waste 100%. Then recycle 80%. Then scientific disposal of 100%. Cost recovery 100%. Redressal of complaints 80%. Efficiency in collection charges 90%. And processing of waste, the municipal solid waste 100%. So we set very high standards for all of us. Then it talks stormwater drainage. Stormwater is the water coming during rainy season. 100%. That means the entire city must be covered with stormwater drainage, and there shall not be any area in city which is waterlogged, 0%. So what we do is now we use 4 criteria. We need to have a selection of recurrence interval and what is the frequency of floods for which used for design of the urban drainage structure. So we find knowing the economics with how much money I have, the public health construction, and the nuisance value, we select the recurrence interval. Recurrence interval for what type of flood I design my system. Then from the meteorology, I select the design storm. From the hydrology part, I estimate the peak runoff rate of storm hydrograph. Using principle of hydraulics, I design the size of the conduit. So this is what is a common procedure used to design a stormwater system. Now we also talk about best management practices. That's very important in the cities. Best management practice, in short, today we use the word BMP very often. Is a stormwater control system is economically and technically feasible to reduce the quantity of pollutants to meet the water quality goals. So the idea is the water quality of the receiving water system must be good. So we should have a quality control of the stormwater. So typically you find a stormwater retention ponds, a treatment wetlands, then stormwater reuse, etc. We use something called a swale. Swale is a vegetated open channel. You have a drain by the road, and you vegetate it instead of lining it, and that is very, very effective and sustainable. So basically, we have two types of master plan practices. One is non-structural, where you don't construct any structures, but we keep good housekeeping. Other one is structural, which involve construction facilities for treatment to improve system performance and to reduce the pollution discharge into the receiving water. So you find many things could be done here. That we have to know for designing this, we have to know the surface water availability, how much water available from the streams. Then we have to have a design storm concept. We talk about stormwater detention, culverts, stormwater retention, swale design, the reuse of stormwater, storm sewer design, and water quality improvement. That's where all these are used. So urban drainage system basically have to collect, transport, and the stormwater away from human settlements. So that means the human settlement should not get waterlogged. We collect the rainwater, stormwater, and transport them away from the human settlement so that we protect the health, quality of life, and enable daily urban activities. In addition, the stormwater runoff, they also must collect wastewater derived from domestic, commercial, and industries. Now, in any city, we find there are two types of drainage system. One is major drainage system, surface runoff, overland flow, natural drainage channel. That means any stream which is there naturally, it could be used as a major drainage system. Then you design a separate drainage system, a combined drainage system, which you call minor drainage system. Then we could have an underground drainage system, which is expensive. So we could have a surface channel, a detention basin, swales, etc. So underground system is something which is very expensive. We don't do it. Then what we plan is we control the source of water. That means any water which comes from the rooftop must be collected, and then don't allow it to go to the municipal drain, etc. And use on-site, off-site technologies, infiltrate the stormwater, use constructed wetland. I'll be talking about it a little later. So we have detention pond to detain water for some time before it being discharged into the drainage system. Now, let me just quickly talk about swales, which is now picking up all over the world. A swale is a vegetated open channel that infiltrates and transports runoff. A few cities are having these swales, and this when you have a drainage system in a city which are lined with concrete, they run faster, and all the sediment also goes. Whereas instead of lining with concrete and cement, I vegetate. I show you the pictures. So there's a low velocity. So when the low velocity prevents transport and loss of soil, and vegetation within the swales are effective for removal of solids and retention of soils. So we use simple Manning's equation. We can find the length of swale, and I'm just skipping some of this. The stormwater that is collected can be reused for various purposes. So stormwater is a resource which can be used, not something to be thrown out. So you find when stormwater reduce the volume of discharge stormwater, therefore decreasing the loss of potential freshwater resources and decreasing the pollutant discharge from the stream. So stormwater can be reused for a number of purposes, like irrigating open lands in the city, recharging the groundwater, supplementing water for cooling purposes, supplementing car wash water in cities. Now everybody is a car. Then create wetlands, supply water for agriculture use. So you find this stormwater can be used for many purposes. Then we use the non-structural BMPs where we don't construct anything, but we increase the housekeeping. So this is today advocated that improve the housekeeping of the system. So some of the practices reflect general goal to get ordinary people more actively involved in the protection of our environment. So basically, it is to prevent, to reduce reduction of pollutant content in the stormwater. So for examples will be organized collection of household chemicals, transport of chemicals and hazardous waste, street drainage design standards, active contact industrial discharges, etc. Then we have to have source control. More important today is the source control. And we use local interception, include maintenance of natural interception, infiltration areas, swales, control of purvase areas, use of retention bins, etc. And have a direct drainage path following the contours, implement erosion and sediment control during construction, then control of land use activities, maintenance measures including street sweeping and regular cleaning of pits. So many controls can be incorporated into the drainage system. We can filter stormwater, including vegetated landscape waterways, trap pollutants in different type pollutant, reduce peak stormwater discharge, and utilize urban lakes as pollution control centers. Then you ought to also manage the receiving water. Very important. All the urban wastewater, stormwater should not enter, should not corrupt, pollute the receiving water. So we have to have an integrated design of facilities. We have to manage fisheries, including stocking and fishing control. Use the right type of plants for wastewater control. I'll show you some of these. Now, what we talk about today is what we call a water-sensitive urban design. So any design that you do should be sensitive to water. So there's an approach to integrate stormwater, groundwater, and wastewater with the land design to make efficient use of the water net minimize energy. So we want a ecological sustainable development. We have water sensitive design, urban design and built form, urban water cycle. Then we talk about potable water conservation, wastewater, stormwater. So that's what we talk about today as the water sensitive urban design. Now just some pictures. These are all in many pictures from our country. We have sediment basin. So all the sediment which comes are collected there. We have a swale. Here is the vegetated open channel. Instead of lining with concrete, we line with glass. So small slope, so water goes slowly. And then we have a bioretention basin, the water is retained. And these plants which are grown has a capability of purifying the water. I'll show you a small picture about that. Then we construct a wetland. Here we can use the aeration and the biological processes to purify the water. Then we got infiltration system and sand filter in the roads. It's a completely making porous. I have separate chambers for sedimentation, filtration, overflow. So this is another thing which we try to introduce. Then we use ponds and lakes and lots of green roof and garden that we use here. So this is something which we are now trying to improve the environment. So then we also have certain source control methods to reduce runoff in urban areas. Use of splash pads, extension of pipes, soakaway pits, seepage trench, porous pavement, etc. Just here. So this is a pipe coming from the top, and it is allowed to splash, and it get inside here, or extend the rainwater pipe and allow the water to go here, and use the landing between the staircase and porch to store water. You have a pit away from your building to soak, or if the contours permit, take water on both sides and infiltrate here. These are some of the source control techniques that you have. So you find there are many stormwater management practices that we have here. We can use porous pavement. We can have stormwater planters, swales, vegetated filter strip, rain garden, wet pond, etc. So basically, we talk about urban landscaping, which helps to manage stormwater, and we have to choose appropriate facility and size it depending on our budget, our landscape, and the hydrology. So you find the urban landscaping is very important. Today is very important. It depends on the nature of the city and its terrain, and it has become very prominent today to manage stormwater, and vegetation provides filtration and root uptake thing. So just to give a picture here, we have porous pavement. We have rain garden in the areas. We prepare some place which and grow plants which can grow in excessive water. Rain garden. This is a swale you see here. Instead of having a channel, we lined with concrete, we lined with vegetation. So there's a swale here, and wherever the water gets collected, we construct something like this and have water intensive crop. We call it stormwater plant. So for this, we need to assess the site, how much is the runoff that's coming, and what is the space available for stormwater facility, choose a proper facility, and size it. So I'll just show you some pictures. So we can have a direct runoff to landscape. You can have a swale, direct parking lot runoff to landscape, manage runoff from driveways or small playways. At residential level, stormwater drain at the starting point of its generation, the condo runoff can be reduced significantly. That means if I house and I do not allow my rainwater to go into city, the water can be used by my house. That can be done. So, for example, you can have a landscape the areas, where reduce the imperviousness. These are some of the pictures that we have where we don't make good roads, we just make these type of things. There's a place where the rainwater can infiltrate. So in all this, we should involve the public and community leaders so that the largest community of residents and service users will get benefited. Use slum dwellers because they are the low-income communities who come and who settle in the areas of low-lying areas during flood. Then we discuss the land developers so that new development for housing or industry can take up. Farmers are also very important because outside the city areas, they could have agriculture interests. Environment is very important because we have to maintain the quality of water and conservation of natural habitat. And local politicians are very important because they take priority issues in the government. So typically, if you have impervious surface here and you have a landscaped area, so you just look at the area, 50% of this will come landscape. So all the water will come here and they get drained off. That is something which we are encouraging, that 50% of the impervious area should be landscaped so that the water will not cause floods. So the rain garden that I talked about, it reduces the stormwater management cost, increase in groundwater recharge, real estate values increase, community gets involved, and street planning and reduction heat island is there, and local microclimate gets improved. So typical, rain garden, these are all landscape where these plants are grown with rainwater alone, and these plants do not require much maintenance. They live in high water, they're highly water intensive. Then you can add store level, it's completely paving. You have some place where you can have some plantation there. You can see some of the people that the footpath could be porous lines of water can enter into the ground. We find the whole thing is done like this. In the campus where I'm working, IIT Dharwad, we have implemented many of these things. Probably, if time permits, I can show you some pictures of my campus as well. See, these are all the rainwater harvest structures. You can see here the swales. So when you have this do this plantation, you have to have certain guidance. One is, do not plant trees or shrubs which have long tap roots close to the drainage facilities, because the long tap root may affect the foundation. So plant trees and shrubs at least 4.5 meters from the perforated pipes. There are pipes, you put it there far away, and 7 to 8 meters from any tall structure, and we should have a stabilization method for turf clean reinforcement. Use as far as possible locally available plants. Do not bring plants from elsewhere because they look nice. So native plants are defined, and those species that evolved naturally live in a particular region. So if I'm doing some tree plantation in my area, I should grow plants which are native to a particular region. So just give an example. If you have a native plants, you find the roots go deeper here. When they go deeper, they loosen the soil. They lose the soil, the water percolates. So these are typical native soil. And here, when I use this, when you use, non-native plant, you find their all roots are here only. So the water doesn't go inside, and so whereas here you find the roots are here, has gone as much as this. So as whenever you do any landscaping, use plants which are native to your place. Now IIT Dharwad has certain interesting thing. We use what we call a nakshatra vriksha. See, every one of us born has a birth star. There are 27 stars, and each star is linked to a vriksha plant. So whenever you plant a tree, we find out the star of the birth of the person and grow that tree. The whole campus is like that. The Prime Minister of India visited our campus. We grew tree based on his star. The Vice President of India visited our campus. We planted a tree for his star. Recently, we had Finance Minister Nirmala Sitharaman. They also planted a tree. So you find a lot of these things could be done, but in India, landscapes are not much popular at present, and a lot of work has to be done regarding the Indian situation. So that is what is happening. Now, this is an experiment I did in my earlier institute, Warangal, where there was a problem of stormwater management and wastewater management. So this was done about 20 years back, and I feel very happy that it's a very good work that I've done. So we did a research area. Can you see me? Can you see me, please?
No, sir.
Yeah, the power, just give me 2 minutes. There is power failure. Just give me 2 minutes. Just give me 2 minutes. There's a power failure here. Let me connect my. I'll stop sharing and then share again. Can you see the screen now?
Sir, no.
Yeah, just 1 minute. Can you see my screen?
Yes, sir, it's visible.
Yeah. So I may not be visible because of this power problem. Doesn't matter.
No issue, sir, you can carry on.
Yeah. Yeah. So this is an experiment I carried out 20 years back. So I said this is a drain which carries both wastewater and stormwater, and there's a big lake here, and this was a study we carried out. So what we did, so it carries both rainwater and stormwater. We put some barricade across it. And we widened that channel. The moment we widened the channel, we find all the floating materials came up. We removed all the floating material, and then we constructed a wetland for the size of which was about 100 square meter for a quantity of 5 cubic meters per day. So it's a pilot study to show that it is effective. So we took 5 cubic meters per day. And so this is the construction stage. After it's constructed, it's in the stage of construction. And you find this a very cheap type of construction. It cost me less than 80,000 rupees for 5,000 cubic meters, for 5,000 liters. So after this, it was constructed, we filled up with the clay soil, and then we planted a particular type of plant, which is local available. These plants, the type of family of plants, are known to enjoy wastewater. And we did a small study in the laboratory to find out how many plants are to be grown. We found 4 to 6 plants per square meter improve the water quality by 90%. So we planted this and we allowed the plants to grow. And this is after 3 months of plantation. And these plants grow very fast. So, and then that's a channel that we have here. And that is ladies, Dr. Margaret Greenway, professor of environment in Griffith University, Australia. She came to see my studies and you find the results. So we monitored many parameters on this. And let me take care of one parameter, for example, here. Let us take one parameter, the BOD. So we monitored this treatment plan for 15 months, 12 months continuously, and 3 more months overlapping, or covering all the 4 seasons. We find the BOD value from 270 to 250 in the month of April, May, June, July. And then that's how there are 19 parameters we monitored. So this is the raw wastewater in the drain. Then when you widen the drain, the floating mill came up, the BOD reduced to from 250, etc. It reduced to this level. That means almost half, it reduced to half of its size. Okay, can you see this? I'm visible, right? My slides are visible.
Yes, sir, you are visible.
Yeah. The power is again gone. So you find the BOD level reduced from the previous slide you just see here, from 270 to 50, it reduced to 166 and 150, that range. Then after the plant washed through my plants, you find the BOD level reduced to this level. That means this is within the permissible limit by Central Public Health Engineering, Central Pollution Control Board, that the water can be released can be released outside. And you also find that after treatment, there is dissolved oxygen here. You find the last line here, there is dissolved oxygen. Whereas the previous slide did not have any dissolved oxygen. So what happened is that in just 15, I could reduce the BOD to the permitted discharge standards, and it also improved the water quality. Now these plants have an interesting character. These plants attract dragonfly, and dragonfly eats mosquitoes. So you find when these plants are growing, it has ecosystem services that the entire mosquito that come are eaten by the dragonfly which is there, and you also improve the dissolved oxygen. So just to compare, only summer months you see here, the raw wastewater 270 to 250 this range, and the inlet wastewater widening, it reduced to this level. And finally, I could bring down this without using any power or chemicals. So this is a natural treatment of wastewater, very sustainable. And this is part of a PhD work of one of my students. Okay, now you find the removal of pollutant percentage or efficiency. The BOD efficiency removal is around 92, about 82% everywhere. So you find a very efficient system that we have. So we show that free surface wetlands are effective, viable for primary settled wastewater treatment system, especially in a country like India. Now quickly let us see how we manage waste in our country. So we have some abbreviations which I just picked up from various places. Some perceptions of waste management. One is called NIMBY. When I have waste, I don't throw it behind my backyard, but I throw it behind my neighbor's backyard. Not in my backyard, it's called NIMBY. Not in my elected term. No corporator wants to improve waste management in his elected term. Banana, there's build absolute nothing anytime near anybody. Catnap, cheapest available technology, narrow body prosecution. These are all the terms which are used for waste management some 10, 15 years back, but today is changing. So countries like India, what happens? the massive migration of the population from rural to urban. So the moment the people come to urban, there are new consumption patterns, production technique, expansion of human activities. So all types of waste increases, and we don't have laws, strategies, rules which encourage reuse, recycle, reduction. And our estimates are inaccurate of the waste produced in our country. Then the health environment hazards caused by waste not addressed. So, and we do not have data about urban solid waste, hazardous waste, biomedical waste, or e-waste. Even some data is available, but even that is not complete. Then we find no estimates or tentative figures exist for construction demolition waste, packaging waste, mining waste, waste from end-of-the-life vehicles and tires, agriculture and forestry. So we do not have any estimates of we have and how it affects our human health. Now, just to give an idea, this is a data of 2021. We find annual waste generated is around 62 million. Out of plastic waste is 5.6 million. The biomedical waste is 0.17 million tons. Hazardous waste is 7.9 million tons. E-waste 1.5 million tons. This is what data. That means approximately per capita waste generation in Indian cities ranges from 200 grams to 600 grams per day per person. Out of which 43 million tons per annum is collected, 11.9 million tons is treated, 31 million is dumped in landfills, and only 75 to 80% municipal waste gets collected, and only 22 to 28% of this is processed and treated. So we have a collection system, we don't have proper treatment system. So waste generation will increase from 62 million tons to about 165 million tons by another 5 years. Now, this waste which is there, untapped, can be used for some conversion calculation. It can generate 439 megawatts of power from 32,890 tons per day of combustible waste, including refuse-derived fuel, 1.3 million cubic meters of biogas per day, or 72 megawatts of electricity biogas, and 5 million metric tons of compost annually generated to support agriculture. So if we use our waste properly, this is all that we can have. So our solid waste management goal should be to provide a hygienic environment, and it also should create create a barrier to break transmitted disease, avoid pollution of environment, so that people can lead a healthy and productive life. The natural environment is protected and enhanced by minimizing resource consumption and closing resource loops.
Hello, sir.
I think so. There is some network issue. Okay, he left.
Yes, sir.
Okay, Love, please call him again.
Yes, sir.
I will request all the participants to wait for 2-3 minutes. I think so. There is some network issue from the speaker side. So we will connect shortly.
Hello. Hello, sir. Just talk with the speaker. Sir said that there's a power failure and he will come back in 10 minutes.
Okay, so, okay.
Yeah, I request every participant to stay connected. We'll resume as soon as sir comes back. Hello, sir. Am I audible?
Yes, you are audible.
Your mic is mute right now.
Uh, Jay, sir, your mic is mute right now.
Yeah, you can see me now?
Yes, sir. Yes, sir. Your screen is visible and you're audible.
Yeah. I'll just share it again. Am my screen visible?
Yes, sir. Yes, sir.
Is it visible now?
It is visible, sir.
Yes.
Actually, we can see your browser. You're sharing your browser. Yeah, now your PPT is being shared.
So I was just telling that, can you see me? Can you hear
Sir,
it, right?
can you convert your PPT into presentation mode?
It is not presentation mode. It is in presentation mode. Is it not presentation
Actually,
mode?
no, sir. Yes,
Yeah,
now it is there.
actually, yes, sir.
Yeah. So you find, so I said earlier that the best is to source control, source reduction, and the least preferred is landfills. Unfortunately, we are giving more landfill everywhere in source reduction and reuse. So this is a picture in most urban areas in our country, many places. Now, what is happening is the industrial waste management. I will take some pictures from some of the good examples. Mumbai, you find industrial waste management. You find here that 12 states contribute to 90% industrial waste generated in India. Most states have industrial waste management facilities operated by private sector. Notable growth, but require further monitoring. Successful because of the PPP structure and artificial polluter pay. Regulator is a facilitator to establish plans, very well outlined guidelines and proven technology, waste category well defined. So this is happening in our country, the industrial waste sector. The another thing which has been happening in the past 25 years is the biomedical waste management. So in India, we find there are 7 lakh beds which are catered to out of 1.3 million available beds. So very, very poor, management of biomedical waste. More than 100 operating facilities across the country. So there's reasonable compliance with the cities and large towns. However, technology improvements are required. A success factor is polluter pays. That means for any hospital which pollutes, they pay. The untreated waste is generated in far and remote places where the viability of facility is difficult, but most hospitals are contributing to this biomedical waste management system. The municipal waste sector is in a very big mess. The current waste management practices are very primitive. Door-to-door delivery, primary collection is unhygienic and unorganized. Secondary collection is open from open points, uncovered bins, and partly organized. Transfer station almost non-existent. Water operations are primitive. Then you got tertiary treatment, partial, unhygienic, uncovered, and open trucks, small volume trucks. Just look at this picture. You look at the truck. A truck which is carrying solid waste also looks like a waste truck. In fact, the major cost in solid waste management is the transport. So we generally recommend when somebody comes to us that we use most fuel efficient vehicle. But then you look at these vehicles, they are very, very, they look like garbage. Okay, so you find here treatment disposal, mainly open timing, which is not accepted. Now, legislative framework demands comprehensive treatment. Less than 5% is scientifically disposed of. Techno-commercial viability is not established. Then there is no money. There are no people already give money. And very poor compliance. These are some of the pictures in different parts of India I've seen here. Now, what is happening? The present situation is on the left-hand side. What is required is here. This is the present situation, the type of trucks, and what is required is this. The trucks are like this, but we require this type of things, which is now slowly coming up in the country. Okay, you see here how they are dumped here, but what is required is like this. You find many, many pictures where, the solid waste management, transfer station, transportation are done. Yeah, and you find street sweeping. Again, there's a condition here. We use, this is a city of Ahmedabad, where they use a excellent vacuum cleaner sucker, and that's what is happening in many smaller cities in our country. And you also find the present they're burning, and what it can be actually collected neatly here, and then you can use plantation like this. Okay, so you can also develop areas like this. So you find that the municipal solid waste sector needs disposal requires a lot of improvement. Then we talk about plastic pollution. It is found everywhere, from top of mountains to deepest portion of oceans, and it's accumulated plastic objects and particles of Earth's environment that adversely affects humans, wildlife habitat. Plastic that act as polluters are categorized into micro, meso, or macro debris. And plastics are inexpensive, durable, so they are adapted to all different purposes. So manufacturers use plastic over other materials, but the chemical structure of these plastic make them resistant to many natural processes, so they are slow to degrade. So we find these factors allow large volume of plastic to enter the environment as mismanaged waste and for it to persist the ecosystem. So the quantity is about 1.1 to 1.8 million tons of plastic weight enters ocean every year. By 2050, there will be more plastic than fish in the ocean by weight, according to some of the calculations that we have done. Degraded plastic waste can directly affect human beings, though both direct consumption, indirect consumption, and various hormonal mechanisms. So a recent survey shows 375 million tons of plastic waste is produced each year. 51% is in Asia, and China being the world's largest producer. So you find out of the total plastic produced, 51% is in Asia. And of this, only 9% has been recycled and another 12% incinerated. A large part of plastic waste enters the environment, which affects the ecosystem. There have been efforts to reduce to make it plastic free, but then to reduce the consumption and to encourage recycling. And actually, this increased during COVID. The amount of plastic and waste disposed increased in the past few years, COVID and post-COVID years, due to increased demand for protective equipment and packaging materials. Higher amounts of plastic ended up in the environment, especially in the oceans, mostly plastic from medical waste and masks. So several news reports point to the plastic industry trying to take advantage of health concerns and desire for disposable masks and packaging to increase the production of single-use plastic. Efforts to reduce the use of plastics, to promote plastic recycling, and reduce mismanaged plastic waste or plastic pollutions are going on. There are some examples. On 3rd March 2022, 3 years back, representatives of about 175 countries met and they took a pledge to create a legally binding agreement to end plastic pollution. The agreement should address the full life cycle of plastic and propose alternatives including recyclability. There was an intergovernmental negotiating committee which was created by the end of 2024. And this agreement should facilitate transfer to circular economy, which will reduce the greenhouse gas emission by 25%. The concerns are the main plastic producers continue to lobby government to refrain from imposing restrictions on production of plastic and to educate voluntary corporate targets to reduce new plastic outputs. World's top 10 plastic producers, including Coca-Cola, Nestle, and PepsiCo, have been failing to meet even their own minimum targets of virgin plastics. India, what we have done, we started banning the single-use plastic from 2nd October 2019, 6 years back. We request avoid use of plastic bottles to provide drinking water during governmental meetings. And in fact, none of the government meetings are plastic bottles. So they give water to provide water that do not generate plastic waste. One example is the National Games at Trivandrum in 2015. They had a green protocol. All venues were zero waste, disposable, free use of reusable tableware and stainless steel glasses. Providing refillable steel flasks to athletes, these activities stopped generation of 120,000 tons of disposal waste. Bangalore banned plastic for all purpose other than milk in 2016. Maharashtra effected ban of plastic and tobacco products in 2018. Fines were imposed. Last year, we began to implement countrywide ban on different sorts of plastics to achieve climate change targets. And there are 8,000 additives, part of 1,000 times more powerful than greenhouse gases than the carbon dioxide. So what we have to do now is we have to take things from linear economies. What we do is we take a material, we make something out of it, we use it and throw it out. That's called linear economy. Today, we are talking about circular economy, where we take some material, make something out of it, use it, and then recycle it, and then it goes like that. And then ultimately, it becomes waste. So this is what we call circular economy. But what we are now trying to do is a recycle economy. Take, make, use, and then reuse, return, recycle, repair. So that is what is going to happen. Today, this is what is going to have. So from linear economy to circular economy to recycle economy, this is what is making our country very sustainable. This is what we are now encouraging people to talk. So challenges in waste management are waste collection plan, waste transport plan, waste storage plan, waste treatment plan, waste utilization plan, and revenue generation. That is something which we are now facing. So we have to be, I just show 5 minutes. This is the main building. Our goal is to reach net zero campus by 2030. This here main building here, the two buildings, the center portion is a glass portion. That's where the director of the institute stays. So here our concept is energy of all types imported should be equal to or less than the energy exported. So we import electrical energy, LPG, petrol, diesel, export electrical. That means I'm going to have a completely 100% solar powered campus. That's what you're doing. And net water consumed to be equal to or less than the internal water harvested. So we are harvesting the entire rainwater on our campus. All types of waste generated are recycled in a campus in an eco-friendly manner. So what we talk about is we use the entire campus. We use green materials, green technologies, recycling of waste, recycling of water, green energy for cooking and power. The green energy comes from solar, biogas, and biofuels for transportation. We do the entire rainwater harvesting and used water recycling. Green waste management, we do segregate the waste, biodegradable for composting and biogas, non-biodegradable waste for fuel, e-waste for recycling, liquid waste for treatment and reuse, human waste for biogas, medical waste for incinerate. So that's what we are doing. And transportation, we have banned motorized vehicle for students. Every student shall walk or go in bicycles. Solar vehicles are available. And we also have electrical vehicles running on the campus to pick up students who are in need. So green products that we are using should be biodegradable. We use mostly cotton clothes. Should be locally made. We use a lot of Dharwad made products we use. Should give employment to many. Handloom we use here. Should benefit the poor. Made out of renewable resources. And we talk about climate change, energy crisis, water crisis, waste legacy, or legacy waste. That's what we are now contemplating. So just to see the campus here, this is the main administrative building, and this portion between the main building here we have the director's office, which is on all sides glass. You can see the entire campus. So that's the campus that we have here. Inside the campus, we've got 63 acres of reserve forest area, and some forests already existing. And we've got 3 areas, the residential zone where faculty stay. The yellow color is the academic area, and the blue is hostel area. And we've got convention centers. All, that's the type of the campus that we have here. You can see here, this is a lectural complex here. You see here. This is a lectural complex, circular shape on the top. There's a ramp up to the top floor, and the roof is, transparent. We can, enough lights there. We have constructed, all the rainwater has been collected and constructed and it's stored within the campus here. And there's a lectural complex. you can see here, we can go up to the top floor by ramp. And this is the library. We have a natural ventilation, and these are academic areas, academic blocks that we have. And we maximize the utilization of daylight hours. And 50% of the areas daily with adequate illumination. That means our entire campus, 50% power during daytime come from natural sunshine. And we are going to have the solar photovoltaic system for the whole campus. Entire campus is going to get the power from solar. We will not be getting any power from the state government. So you find that we have 590 million liters of water for 10,000 people that we will be having. And right now we're harvesting about 320 million liters and 20% losses. So this is being happening. So reduced our day demand by 20%. Recycled used water after treatment. So demand reduced. The evaporation percolate losses are reduced. That's what we have done. That's the campus here. Now some more. The collection of rainwater harvesting is being done here. To see that the campus has net zero energy, net zero water. So that's how here we have to design the lakes here. 3 lakes on the campus. And so we also encourage people to reduce water consumption, unnecessary waste is reduced. And we always say, think before use. All products we consume for water products, example, 1 liter of the PET bottle consumes 2 liters of production. Stormwater drainage should be kept clean. And this is what I showed you a little earlier. From linear economy, we're going to circular economy, recycling economy to circular economy. That's what we are doing now. And we have put all interesting boards everywhere. Do not litter, keep the campus clean, use dustbin languages, and untreated sewage pollutes the stream and underground aquifer. So we see that things around. This is our waste management system. The entire campus is treated here again using a natural treatment system, which I showed earlier. And after treatment, the entire water is used for maintaining the garden. So that's a treatment plant that we have. And you also see we did not cut any trees. We completely, took out the trees, carried it and transferred elsewhere. So trees which are very old, 20, 30 or 40-year-old trees, were transferred elsewhere. And so we have done this. The many trees are transplanted. They're all very successfully growing. And we use the students many times here. These are trees on the campus already. So the idea is to make this a sustainable campus. Pictures here and there of different parts of the campus. So some of the questions that we ask everybody, it's for you people also who are attending this. How much water energy do I use every day? Where does it come from? What kind of food I eat? Where does it come from? What do I throw away? Where does it go? How do I travel? How do I build my house? What is the ecological footprint? These are questions we ask ourselves so that to make the campus very interesting. And this I showed you earlier. So we have to have this food for thought when we talk about sustainability, that we need to be open-minded to the reality that the future won't be like our recent historic past. We don't overreact, but we should start now to incorporate the flexibility we'll need to deal with the impacts of climate change on our water resources. So people everywhere breathe the same air, share the same seas, live together on the land. People everywhere will learn, plan, work, care, can save the earth. So let us live green, stay green. Let us not have this type of teamwork. Let us show high level of integrity, motivation, honesty, innovation, sincerity, hard work, leadership, and inspiration. And I stop here. If there are any questions, you can ask me now, or if no questions, you can please feel free to send an email to me, which is given at the bottom. I will definitely answer email in 1 or 2 days. And to finish my thing, this is the last slide that I have, one of my pet slides. This is a lake in Kerala, city of Calicut in Kerala, where I was working for 5 years. And we cleaned the lake in the city by using the treatment that I showed earlier, use a Typha family of plants. And this water got improved by 90%. So these are my hands. I'll take the water, and someone of my scientists click this photo and use this as a slide. I got a national award for this, for West Island Lake Protection. Thank you.
Thank you so much, sir, for this wonderful session. Now we will move on to the Q&A session. If anyone have any query, you can type it in the chat box, which I will read for you.
I'm sorry, there's no power here, so there's some power outage unexpectedly.
Yeah, Kanya, I've already, in fact, put it on the chat box. You can have a look at it.
Yes,
Yeah,
sir.
yeah.
Yes.
Do I require to spell it out?
Uh,
You will read for me.
uh, so just 1 minute. Yes, sir. So we have a question from Colonel, sir. With the population disparity in comparison, we with 17.5% and budgeting of merely 0.5% of GDP. In comparison to developed countries, are spending anything between 1 to 1.8% of GDP. How do we look at success of Amrit and UJJM and national water policy? How can we reduce NRW to less than 15% as targeted in government initiatives?
Thank you for this question. Really beautiful question. Now, what is happening is we look at the Indian knowledge system, how we were managing water starting from our Harappa Mohenjo-daro ways to during Gupta period, Maurya period, etc., where a lot of community involvement is there. The moment people feel it is their water body, make them feel belongingness, many of these get improved. We have seen when people get involved in managing the water resources, lot of non-revenue water gets reduced. It has been happening. I've seen it physically in many parts of the country where the success of these programs have been largely due to involvement of stakeholders, involvement in communities, a joint management between the government and the local bodies and the public. So that whenever the public is involved, like in the past, this has been successful. So we'll have to motivate people to get involved, make them feel it's their program. It is not their government, their property, their a sense of belongingness of all the water bodies. I've seen many of the water bodies being rejuvenated by the people. As in the past, in the olden days, people used to give in terms of money or in terms of labor. So today, some work is required. People come and give the labor to see that the system gets improved. It has been happening. There is a drastic change the past 10 years of people involvement, community participation, and people's involvement in the management of the Water Body Act. So this is going to be very successful.
Sir, can you please update us on if other than the government initiative, what is the participation of PPP and the HAM?
See, the many of these, what do you call CSR activities are getting involved in this. Many of the, in fact, our Dharwad campus, we got about 8 crore rupees from ICICI Bank from the CSR funds. And
Yes.
they are now taking a lot of pride in saying that this campus is theirs. In fact, our idea is, to make IIT Dharwad campus a model energy. So they are helping us. And we find the moment people are convinced, students have to be convinced. They are
So I think Professor Jay sir is having some internet issues. So I hope your queries is answered. So so we are connecting with him. He will join in 2 minutes. So participants, this is the last question for this session. With this, we conclude our Q&A session. I would like to extend my heartfelt gratitude to our distinguished speaker, Professor KV Jayakumar, for his enlightening session on sustainable urban water and waste management. Thank you, Professor Jayakumar, sir, for emphasizing the critical role of sustainable urban water management. We now will send you the attendance form, which I request the participant to fill. And with this, will now transition immediately to our final session of the evening, session 8. Also, thank you, sir. If you have any, you can, sir, if you have any ending words that you want to end the session with we are open. So you're muted.
Kanya, are you talking to me?
Yeah.
Yeah.
No, I think so. We can. Okay.
Yeah, can I close up?
Yes, sir. Yes, sir.
Yeah. I think all of us who attended this meeting today will take a sort of pledge that we will do anything sustainable. We will reduce waste. We'll refuse things which are non-sustainable products, and recycle, reuse, recharge, and make our place a very healthy place to live. So let me wish you all the best, and Jai Hinds. Yeah.
Thank you so much, sir. Thank you.
Yeah.
Thank you, sir.
Thank you.
Thank you so much, sir. With this, now we'll move on to our second session.
So shall I sign out?
Yes, sir.
Who is the next speaker?
Sir, so next speaker, we have Mr. Manchanda, sir.
Yeah, then I think I shall take out because my network is issue here. Yeah,
Totally
otherwise, I would have loved to continue.
Thank you so much.
Wish you all the best for the course. Yeah.
Thank you, sir.
Thank you very much, sir.
Thank you.
So hi, good evening again, everyone. Heman, sir, are you with us here?
Yeah, hello, I'm there. Thank you.
Good evening, sir.
Good evening to you and all here.
So as we move on to our second session, that is on structural health monitoring and instrumentation, digital solution for sustainable infrastructure management. This, sir, I'm so sorry for this, sir. Can we start the session?
Yeah, please, why not?
Thank you, sir.
Okay. So let me share my screen.
Sir, just 2 minutes. So this is the practical and digital application of the structural longevity principle we discussed. With this, I introduce today's expert of the session, Mr. Heman Manchanda, sir. We have a distinguished technical leader with deep domain expertise in complex infrastructure to guide us. Mr. Heman Manchanda is the national manager at ATES Consultancy Division of Aimil Limited and a distinguished professional with over 22 years of experience in geotechnical engineering and tunnel design. His career demonstrates significant contribution to national standards. He has been instrumental in India's major infrastructure projects, including the Delhi, Jaipur, Agra, and Lucknow metros, as well as the USBRL tunnel project. Mr. Manchanda sir has been instrumental in pioneering innovations such as reinforced earth wall technology and stacked tunnel design in urban environment. He is a postgraduate from IIT Delhi and is an active member of key professional bodies like the Indian Road Congress and Indian Geotechnical Society. With this, I welcome Mr. Heman Manchanda sir to this session. He will now share his insights on how digital instrumentation and monitoring ensure structural health, minimizing risk, and maximizing the sustainable life cycle of massive infrastructure projects. I now invite Mr. Heman Manchanda sir to take the stage for the session. Sir, please.
Yeah, sure. Thanks, ma'am, for your kind introduction. And with this, I'll start my session. I'll share my screen. Give me just a minute.
Sure, sir.
Let me know when my screen is visible to all of you.
Yes, sir, your screen is visible now.
Okay, great. So, good evening once again, my friends. I'm not sure how you have been operating till now, but I'd like you to be very interactive. Just pause me, stop me wherever you want, because I prefer the session to be more of workshops where people have two interactions rather than one-way interaction. And I'll try to answer wherever I can, and in case I'm not able to answer, because no one is perfect, so I'll take a note of your questions and I'll get you the answer for sure with my contacts in the industry. So as you know, I hope all of you are from civil engineering background. So I'll talk some civil engineering terms because I'm also from civil engineering background. The idea for today is that, look, we all are into design of various structures. Okay, and in civil engineering some designs are based on empirical relationships, and some design are based on analytical relationships. So, and when we talk of concrete, when we talk of steel, we have very good analytical relations developed, because this is a product which is developed in factory or at site with rigorous quality controls and compositions which we can vary by designing the mix, and the things are in our control to a larger extent. But when we come to handle the materials like earth, the material like soil, the materials like rock, which are not man-made, which are made by the nature, it has got so much heterogeneity. Okay, we believe that we all our engineering assumptions of isotropy, our assumptions of homogeneous doesn't actually prevail at ground, and hence it is very critical for us to analyze each and every structure by two ways. First is by designing it using the standards available, using the best industrial practices, and then by actually monitoring the engineering parameters at site and evaluating our critical design assumptions. So I'll start with this brief introduction, and first I'll take up that what is the need for monitoring. Monitoring, first of all, what is monitoring? Monitoring is simple, that in a structure I should be able to get the real values of various engineering parameters. Engineering parameters may be deformations, engineering parameter may be stresses, engineering parameter may be strains, engineering parameter may be temperature which is developed in the concrete or in the earth structure, and likewise. So I should know that what actual values are being developed, and for doing this there are certain instruments which are available nowadays, which we can install and which we can monitor at regular intervals to know the values. So when we discuss about need for monitoring, why do we need to monitor any structure? The basic idea is that first is that we should be able to know the safety of our structure, which is of paramount importance. So if I'm monitoring a structure, then I can compare the design values to the values which I am actually getting at site, and then I can have a sign of relief that yes, my structure is safe because all the values are within the predicted design values, right? Second thing is that in case the values are exceeding, then I will get an warning of any impending failure, because the values are approaching the design values, then it may cross the design values as well at certain cases, and then it may certainly fail. The other advantage is that I'll be able to evaluate the critical design assumptions, because if you are all civil engineering graduates and you have soil mechanics and rock mechanics subject, you know the value of phi, value of C varies to a large extent. Even from the same test, if you do the triaxial test, you do under different conditions. CUCD all will give you different values, right? So the value of C and phi and like parameters depend on the site considerations, drainage considerations, loading patterns, and other things. So whatever during the design we assume those values, right? So if we know the actual values, then we can evaluate those critical design assumption, and we can subsequently modify our design based on the actual values which we are seeing there at site. It is also a very good tool which helps us in operational control, construction and operation control, right? And if we know that something is going to fail, or if we get an indication of any warning, then we can take remedial measures to prevent the problem in advance. And also many regulations and litigations issues can be handled if we monitor the values. These all you will come to know more in detail once I go through all the slides, no? Also, we need to prevent the damage to adjacent structures. I like you to give you a very critical example for this. Most of you are living in Delhi or areas around. You have seen that we have a lot of underground metros which are coming up, and these metros are being going under some houses, under some bridges, under some existing underpasses, under some roads. Okay, so we have to ensure that because of our construction, there should not be any damage to the structures which are lying over our construction, or which are lying very close to our construction activities. So how will you ensure that? You have to install some instruments, and then you need to record the values of vibrations which are being transferred. You need the value of differential settlements that are being coming to those structures because of our construction. And if we control these two things basically, then we will control the further damage that may be caused to those structures. Verification of critical design parameters is almost the same thing which we have discussed before. Optimizing design, lying on the same lines. And we need to enhance our understanding of behavior of the structure, which can be done only if we know the exact values which are coming. And it gives us greater confidence to the designer, and we can affect an effective risk management strategy. I'll come down to this, what is risk management strategy, during the remaining part of my presentation. So if you want to plan any monitoring scheme, then you need to answer some basic questions. These are that: why should I monitor? Where should I monitor? When should I monitor? How should I monitor? What should I monitor? And the most critical part is that who should monitor. Because even if I get the best instruments, and even if I place it at the desired locations, and if the person who has placed it hasn't kept it in the right direction or in the right orientation, then I'll not get the right values. For example, if I have to monitor the vertical load coming because of an embankment, okay, then I put a pressure cell there, which is a plate, and it will measure, say, for you as a beginner, I'll say, which is just a weighing scale. Okay, if I put the weighing scale, instead of putting it on horizontally, if I put it vertically, then it will not attract any load. So even though I'll get a value, it will not be the true representation of the load which is coming. So how to install it and who is installing it is the main key. Uh, what are the key elements of a monitoring scheme? First, the person who is designing monitoring scheme should have basic knowledge of the risk which is associated. Yeah, I'm not sure whether you are right now designing based on that a factor of safety basis only, which is called deterministic analysis, because nowadays world is moving to probabilistic analysis and risk based analysis. In probabilistic and risk based analysis, the basic criteria is that we need to know the hazards and vulnerability which may affect our structures, and we need to design for those hazards and vulnerabilities, keep giving due variation to the parameters which may vary. Okay, so we should be knowing what are the hazards and vulnerabilities to the structure. We should be know that what are the patterns and trends of these variables. We should know what are the risks, and we should be able to map the risk to the data available. And then ultimately deterministic or probabilistic analysis is always a question. In our graduation, in our post graduation, as of now the curriculum allows for deterministic analysis only, where we but you will appreciate that the parameters, for example, if I'm taking a deterministic value of C and phi of soil, and there is a big variability in that. Even the boreholes which I'll do at 10-meter interval may show a high variability, and in that case probably we should be shifting to probabilistic and risk based analysis, not deterministic analysis. Okay, so these things are useful only when we do this probabilistic analysis and risk based analysis rather than simple deterministic analysis. Okay, so once we know the risk, once we know the factors that will critically influence our structure, the structure may be any structure. It may be as simple structure as a multi-story building, or as critical as a structure as a underground powerhouse caverns and connecting tunnels. So doesn't matter. The basics engineering principles remain the same. Okay. Then once we know the risk, then we need to design a monitoring and warning service. Okay, which which involves the hazard monitoring and early warning services. For that we should know that these are the right parameters which we need to monitor. We should know that what are the scientific ways by which we can make some probabilistic and probabilistic analysis for forecast, basically, that these things may happen, and how the warnings will be generated, that also we need to thought of. Even if I know that something is going to happen, and if I keep that knowledge to me, and if I don't dissipate that knowledge, then we will not be able to help anyone. So once we know something wrong is going to wrong, there should be a system which dissipates, and there should be a system of effective communication. And after getting the communication, there should be a response capability. For example, I'll take a very simple example. You know that nowadays we are having a number of landslides. So what we are doing is, in many projects the government has initiated a project and we are associated with them. We are installing certain instruments on the probabilistic landslides to give us early warning system. Okay, so if we install that instrument, if I got early warning, and even if I know about one day before that probably next day there is going to be a slide on this road, and if I'm not able to stop the traffic movement in that on that road, then everything which I do is of no use to anyone, right? So we should be having this adequate response capabilities as well to act. So any monitoring scheme, it starts with design of risk knowledge, then to monitor it, then the information which I have got from monitoring should be communicated and disseminated to the people who will take action, and there should be response capability. We need to educate the public in general that if this happens, then what do you need to do? Then only any instrumentation scheme will get successful. It will solve its purpose. So this is an example of the response matrix which we prepare for underground metro structures. But so that we are ready with any situation at any given time of time. So I'll take up more on dam and landslide instrumentation, because these are really critical structures. Multi-story buildings do require instrumentation, but I'll not touch it because that is not very critical as of now in India. So if I talk about dam, what is dam? Dam is basically any structure which obstructs flow of water. And as we obstruct flow of water, we develop a pond, we develop a reservoir which will exert some forces on my dam, on the structure which is obstructing the flow of water. And we need to ensure that this structure is having adequate structural capability to take the loads in all the ways. So dams are basically classified based on the use of dam, based on the rigidity of dam. Use of dam means the dam can be a dam for irrigation, a dam can be a dam for water supply, a dam can be a dam for generation of electricity, a dam can be a dam for saving some areas from getting flooded. So there are many uses of dam, and there are most of the dams are actually multiple usage dam nowadays. The dams are are also divided based on the rigidity. For example, there may be a concrete dam, there may be a rock fill dam, there may be a earthen dam, and there may be a steel dam as well, right? Material of construction is one of the same thing as rigidity. The dams are also classified based on the flow over its top. There may be some overflow dam, there may be some non-overflow dam, and in fact, in the same dam we have an overflow portion and non-overflow portion. I'm sure you all might be quite familiar with these terms, but in case you have any doubt, you can stop me and discuss it on that subject. Okay. So broadly, we'll discuss gravity dams, arch dam, buttress dam, and embankment dams. Gravity dam is any dam. It may be a concrete gravity dam, or it may be a rockfill gravity dam, which resists the forces by the virtue of its weight. That's why we have the name gravity dam. And if we give the shape of an arch to that dam, right, rather than this normal shape you might be familiar with, then we call the dam as arch dam. Okay. Buttress dam is basically a concrete dam. It may be also constructed with a timber and steel dam, but it's really very small dam, not for used for very high head levels, and it has got a buttress. Okay, these are the buttresses to resist the forces. And earthen dam is constructed where we don't have good foundations, and we have the forces, the vertical forces have to be they have to be dispersed at longer sections. There we prefer to go for earthen dam because the cost of construction of under earthen dam material wise is less than concrete dam, but the area and the land required is much wide. You can see from the figure. So these are the dams which I was talking. These are the gravity dams. These are the arch dams, and these are the embankment dams. So let us talk that what we need to monitor in these dams. Okay, as per Central Water Commission guidelines 2018, we need to for any dam which is large dam. Large dam is any dam which is more than 15-meter height. We need to monitor the movement. The movements can be a horizontal movement of dam, vertical movement of dam, there may be rotation, there may be lateral deformation. We need to monitor the pore pressure and uplift pressures, which are very critical for the design of dam. We need to monitor the water level, the seepage flow, the water quality as well, because water quality is an indicative of is a sign of any piping which may be taking place below the dam body. We may need to monitor the temperature, the crack widths, the how what is the nature of crack widths. If there are cracks, then is there any increase in the width of those cracks, or it's constant, or what? We need to monitor the seismic activity. We also need to monitor the weather and precipitation data, and we need to monitor stresses and strains. So areas to be monitored, if you see, so if you there are different areas, different components, I must say, of an embankment dam. One is upstream slope, another is downstream slope, another one is abutments, then crest, internal drainage system, toe drains, and riprap and structures, and slope protection measures. So visual inspection is required almost at all in all the places, but not in internal drainage system, because it's very difficult to access internal drainage system. So we should do the visual inspection of all the other areas. And if we need to know whether we need to record the movements, then the movements are very critical for upstream and downstream slopes. Movements are critical from crest and abutment level as well. But for toe drains, we are really not very much bothered about the movements. Even if some movements happens, I don't care. Same goes for slope structure works and rip wraps. Minor movements are not going to make any big difference, so we don't need to monitor them. Uplift and pour water pressure, similarly, we don't need to monitor for slope protection and rip wrap areas, because uplift pressure is critical below the dam, not at those locations. Water levels is critical only on the upstream side. Downstream side, whatever water level is there, and you don't need to monitor. Similarly, seepage flows, upstream slope, seepage flow is not critical, but for downstream flow, seepage flows is very critical, because it will tell me how much seepage is, how much impermeable or permeable my dam body is actually behaving. For abutment as well, seepage will play a very big role, because the load bearing capacity of abutment will be affected drastically with respect to the uplift pressure and water levels present at that level. Similarly, internal drainage system, we need to monitor the flow to check that whether my internal drainage system is effective or not, and also for toe drains. So wherever there's a function, there's a criticality of water, we need to measure the seepage flow as well as water quality. Why water quality? Because if we check the water quality and we don't find any fines there, then we are happy that our water is not taking away fines with it, and there is no piping which is being developed inside the structure. But in case there is, we find during checking the quality of water that some fines are also coming, that means slowly and slowly more and more fines will come, and my structure stands a risk of failing because of piping effect. So that's why we need to measure the water quality very critically. Temperature measurements are not as critical for embankment dams as they are for concrete dams, but still we measure the temperature measurements at abutments, at downstream slopes, right, and also in the internal drainage system. Cracks and joint measurements similarly are not very critical for other dam, hence we are measuring only at downstream slope and crest, although at upstream slope also many times we monitor, because sometimes there is a failure in upstream slope as well, but not very regular practice. Seismic measurement, there is a guideline which says that we should measure the seismic activity at 4 locations in a dam: upstream slope, downstream slope, abutments, and crest. Although if we monitor practically at 2 of these locations, that should be fine enough. And stress measurement, upstream, downstream, and abutments stresses are critical. Settlement is critical almost at all the places. So this, for example, is an schematic diagram of an earthen dam, which involves a central core, which we design is as an impermeable. You all, I believe, are familiar with dam or no? You have studied dams till now, I'm sure. So I'm talking some terms like that only. So this is the central core which is impermeable, and on the left and right we have relatively permeable material, right? So we install these instruments here. There's a grout curtain. So we install some water level measurement at grout curtain level, and other instrument at foundation level, and also in the dam body you could have seen. Here you see there are some settlement markers which give us vertical deformation. Cell settlement system which again gives a vertical deformation. This is a field extensometer. These all instruments, how what they are, how they work, I'll show in my following slides. Okay. There are some fill extensometers which give us the literal deformation, so and so on. So coming to masonry dam, this is the slide which will tell you what to monitor and where to monitor. So because we have a limited time, so I'll not read in that detail, but I believe you have got a basic idea of what to monitor and where to monitor. Yes. Similarly, this is an arch dam. So you see a number of sensors that we install at different locations in any concrete structure as well. These are the symbols of those samples. I'll share the PDF of this presentation to you. You can go through it at a later stage. You see, we do intensive monitoring of these structures. Intensive instruments are installed because we need to ensure that what we are doing is right. So now first I'll give you basic idea of instruments. What all are these instruments? This is a normal plumb line. You know, A plumb line is basically like a pendulum, you can say. We need to ensure that we need to measure the tilt of a structure. So how will we do that? We install a simple plumb line with a weight at the top of the structure in a pipe, and we let it stand free fall. And with the when the body of the dam will deflect, the center of the bob, the center of that pendulum ball will move on either side of the dam, and it will be deflected from its central location. And knowing the deformation, which is knowing the displacement of that ball from the central line, from the central axis of that dam, we can know the tilt which is coming in dam. So this is normal plumb line. And this is manual, and this is automatic. It will give you automatic readings and it will give you manual readings. This is the pressure cell I was talking now, that vertical pressure need to be monitored. So this is a plate. It is just like the weighing scale which we have in our house, but the technology used is a little different. This is very sensitive instrument. When we construct any structure, any earthen dam or any concrete structure, we install this plate inside at the various locations, vertically staggered locations and horizontally staggered locations. And this is connected to the sensor here, and a wire which is connected to our automatic data recording system, and it keeps on recording the variation in vertical pressures at different point of time and at different stages of construction. This is strong motion accelegraph, which records the vibration which our structure is receiving. And these are the crack meters, 3D mechanical crack meters and 3D electronic crack meter as well, which will monitor the change in width of crack in mutually perpendicular directions. This is the tilt meter, which we install at any vertical face of any structure. It may be dam body, or it may be any other structure. And it will give you the tilt. This tilt is very simple. We have very low sensitive, but we have this tilt technology in our phone also. If we tilt the body of our phone, our screen gets tilted. So there is a sensor which measures the tilt, but the sensitivity is very low. These sensors have very high sensitivity. These can measure the tilt up to 0.001 radians, for example. These are the strain gauges. We install these strain gauges in the reinforcement bars, which is going inside our concrete structure. And then this will give me the strains which are coming up in our reinforcement. These are IPI sensors. I'll describe what is RBI sensors when I discuss all these instruments one by one. This is the load cell with a different basically measuring mechanism. It has a central hole, and it is used to measure the loads which is coming in the rock bolts. You all might be knowing what are rock bolts, I think. And these are the borehole extensometers, which give us the extension of a borehole. Vibrating wire piezometers, which are used to monitor the pore water pressures which are developing under our structures. These are the rain gauges, which you might have studied in your graduation also. A bucket is placed to monitor the value of rain in per hour, or whatever the relative units are. And these are some automations which I'll discuss in the coming slides. So the very basics, the very basic instrument. I'll start with very basic instrument. We need to measure the water table level. For that, the simplest one is that we make a very big well, like you might have seen the wells in villages which we were having, and we simply go there and we simply see the water level. It also gives us water level, but constructing that big a well is not practical for civil structures. So for that, the very basic thing is which was developed was that we just make a borehole, which is, for example, 76 diameter and of the desired length, and we install this pipe in that borehole. And this pipe, you see, is having perforations, small perforations, and we wrap this pipe with the help of a geotextile to ensure that only water should enter in this pipe, and the soil particles should not enter, and it will act as a filter. So what we do is that we dig a small borehole. I am Yeah, like this. Okay, we dig a small borehole, and we insert this standpipe perforated piezometer in this borehole. This is a mechanical type of instrument. I'm starting with the basic first. And then we fill the granular space between the borehole body and this instrument with sand. This space. So that water is free to enter, but particles are not able to enter. So once the water enters in the pipe, it will, after install, once we install this standpipe instrument site, it will take some time, maybe some days, and the water level will get stabilized. And now we insert this water level indicator into this pipe. This pipe is open from one side, and the opening is continuing till the top of ground level. And this sensor is having a circuit which, when comes in contact with water, makes the flow of current to happen, and it gives us a beep. And there is a tape here which is perforated and scaled in meters, in millimeters, sorry. So once we insert it inside the borehole in this pipe, we keep on recording the level of the level of the sensor every with every regress downward. And the moment it gives us beep, it gives us the level of water table. So by doing this, if we do it daily, we can check the fluctuation of water level daily. When it will go up, the beep will come early, and we'll note down the reading at what depth beep is coming, and that will be the water level of that day. So this is a very simple instrument. You see, this is the way how you install it. You can even you can even seal it with bentolite if you want to, if you don't want the interference of other level waters in at that level which you want, but normally sand is good enough. This is a pressure meter. What we it's like the meter which we have in our houses also, to check the water reading, the water reading which we are consuming, no. So it records the pressure which is coming in this pipe. So if we want to know the seepage pressure in a dam body, what we do is that we install a we put a borehole, we install a simple mechanical water drainage pipe in it, and we connect this Borden gauge, we call it, on the mouth of the pipe, and it will give us the pressure reading, that the water is coming with pressure at what point of time. This is a twin tube hydraulic piezometer. The simple. Now coming to automation. First, I discussed a piezometer which needs a manual intervention. A person has to go every time there. He has to lower the water level indicator, and he needs to take the reading. So what are the challenge in that? The basic challenge is that it is requires manual intervention. There may be chances of error. He may take the wrong reading. He may read it wrong, and he may even not go there and simply write the reading. So we don't have any control whatsoever. So to overcome these challenges, we devise automation. We devise the systems which can automatically give us the readings. And this is an outdated system now. I'll discuss the latest system with you. This is the latest system, which is vibrating wire based piezometer. What How it works, I'll tell you like this. The this is the engineering part inside this vibrating wire piezometer. We have a diaphragm here. Okay, the water enters through the filter here, and it put pressure on the diaphragm. With the pressure of this diaphragm, it moves in the direction, in this direction, and the movement causes a change in length of this vibrating wire, and the frequency at which the vibrating wire vibrates, the natural frequency of the vibrating wire, is directly proportional to its length. So by knowing by and this is the plugging magnet which keeps on recording its natural frequency every time. So by reading the natural frequency at any given point of time, gives us the length at that point of time, and this length is calibrated to the pressure, water pressure. So this is the way we have automated the things, and now this is being used extensively for all metros, for all big structures, for dams, for metros, for high-rise building, to give the underground water pressure level automatically, and the frequency can be as low as 100 times a minute. So we can continuously get the readings forever the life of 100 years, for example, of the structure, at a frequency of one reading in every 100th second. So how do we install it? We lower this piezometer simply at the desired location, and we fill it with a granular material to avoid blockage of this piezometer. Okay. And then we plug it with bentonite till the top, or we can use grouting material as well. And now we do a protected cover over the top, so that the cables and the pipe which is coming out doesn't get damaged because of construction activities. And with these, the cable which is coming out is connected to a junction box and a data logger which will record reading automatically. This is the another inclinometer which I was talking, which I say that I'll discuss later. This inclinometer is used to monitor the slopes and landslides to detect zone of movements. How it works? We again drill a borehole at our construction site, and we insert a pipe into it. And this pipe has got internal rails. You see, these are the wheels, four wheels on the sensor, and there is a rails. There are two rails basically in this borehole, in the pipe of this borehole, at mutually perpendicular directions. So these rails act as a guide to our sensor, and this sensor is lowered till the bottom of the borehole and is slowly taken up. So at every zero point 0.5 meter, it takes the reading of the angle at which it is right now. And by plotting the angle from the bottom to the top in a conventional software, which may be as simple as software as AutoCAD or the softwares which come with the system, we can know the tilt, we can know the horizontal position of every 0.5 meter. So we can have the tilt from bottom to up, that how our ground is actually moving with the forces. This is basically critical where we have horizontal forces. For example, when we construct a reinforced or construct a retaining wall, it will move in the lateral direction. Or when you have seen that underground metros, for construction of underground metros, we excavate the central portion of the station. Then to prevent the slopes from failing, we install a diaphragm wall before the starting of excavation. So with the excavation, the forces on diaphragm wall keeps on increasing, and our diaphragm walls keep on moving inside towards the excavated part. And if we install this instrument in the diaphragm wall to know at any point of time what is the deflected shape of our wall from the toe to the top. And that was a manual one, in which a person requires to uh, lower this sensor to the bottom and then slowly bring it up. And it has got all the challenges which I discussed before, which are associated with manual monitoring. To overcome this, what was developed was in place inclinometer, IPI sensors. In that, we fix the sensor at every zero point 0.5 meter. So here, for manual, we have only one sensor, but here we have a number of sensors till the connected to each other. And these all the sensors are having tilt meter in its inbuilt tilt meter inside, and these are connected to a data acquisition system at the top. So at any point of the time, with at the desired frequency, we will be getting the inclination, we'll be getting the tilt. This is now a tilt meter. The difference between this borehole inclinometer and tilt meter is that concept wise they are doing the same, engineering wise they are measuring the same tilt, but this is used to manage to record the tilt in a borehole underground for underground construction. And if you need to monitor the tilt at open ground, then again we have a small tilt meter which we can butt against any wall, any vertical structure, or any inclined structure to give us the tilt at that point of time. So it can be manually done, like in case of this tilt meters, or there is automation also, as I discussed previously. The pendulum, which I was discussing, it is a very simple structure. At the top of the dam, from the top of the dam, we hang a weighted mass, and it will act like with the help of a pendulum wire. And initially when the dam is constructed, it will be at the center of the axis. But when the dam tilts, this weight will go on either side, or the left, right, in the depending on the tilt. It may go to left, it may go to right, it may go to any angle from 0 to 360 degree. And by recording the deflection and the angle, we can know the tilt of our structure at any point of time. Now, the deformation and tilt can be measured either manually or it may be automated by installing those sensors which I have discussed before on this weight. So this is the detail of how to install it and things which I'll not go, right? It may be inverted also. You have seen as inverted pendulum. Similarly, we can have this in inverted also, wherein the anchorage is at the base of the dam and the floating unit or the mass is at the top of the dam. So either way, depends on the feasibility of construction. I was discussing of measuring stresses and strains. So this is the concrete, for example, we have reinforcement gauges. So we will install the pressure cells, which are like this, a simple plate which senses the pressure when whatsoever it comes on it, which is connected to the system which records the data. So we install it one vertical, one horizontal. Actually, we install it in 5 directions because we need at any point of the structure, we are interested to know the direction to the stresses and strains in 5 directions: 0 degree, 45 degree, 90 degree, 125 degree, and one in the direction perpendicular to this plane in which I am talking: 0 degree, 90 degree, and 135 degree. Now these pressure cells are of two type. This is a relatively rigid pressure cell which have rigid plates, which is used for concrete or shotcrete, because the instrument which we have to install should match with the consistency of the material in which we are installing it. If we have to install an instrument in a concrete, then it should be hard and stiff. And if we have to install the same instrument in an earth, then it should be deformable and flexible. So this is the basic difference between earth pressure cell and shotcrete pressure cell. Shotcrete pressure cell is rigid and earth pressure cell is relatively flexible. The behavior and the engineering electronics are the same. Now coming to recording the deformations. Deformations can be recorded in two ways. First is surface deformations and another is subsurface deformations. Recording surface deformation is very easy. It can be done with the help of a total station, as simply that we on a structure we put certain, say for example, I put 100 plus marks on my structure, and every day I ask my surveyor that he should go to site and he should take the XYZ of all the 100 plus marks center point, and once I know the XYZ, I can tell the surface movement of my structure. Very simple, right? Now this putting a plus marks is a very simple way. Then there are techniques which I'll discuss further, which are improved on that putting plus mark. But if in case that will not give me what's happening inside my structure. For example, if I'll take an example of constructing an tunnel. Once I construct a tunnel, there will be deformation at the face of the tunnel. There will be deformation inside the tunnel. There will be a plastic zone and there will be the elastic zone after that. So I need to know what is the extent of plastic zone, what is the extent of elastic zone, and how much are the deformations in plastic zone and at what distance from ground. So how do I do that? I do that by installing multi-point borehole extensometer. How it works is very simple. We dig a borehole, okay, and we install sensors at different levels of this borehole. You see here in this picture, you have 1, 2, 3, 4. So this is 4-point multi-point borehole extensometer. Each sensor will give me the deformation at that particular level. So By doing so, I'll not only get the deformation at the surface, I'll get the deformation at this level, I'll get the deformation at this level, I get the deformation at this level. And if I need to know know how much is the deformation between these two levels, so I subtract the reading of level 3 to from level 2, and this will give me the deformation of the soil layer in between these two levels. So by this I can have the deformation of different layers behind my ground. Crack meter, as I was discussing with you, it will give me the triaxial. Joint meter or crack meter basically are the same. If I install the same instrument on a crack, it becomes crack meter, and if I install the same instrument on a joint, it becomes joint meter. The instrument is very much the same. This you might have very well studied in your degree also. A simple V notch to measure the water flow. So I'll not go into much detail of this. Strain gauges, stresses and strain I was discussing. So I have already discussed the stress and pressure cell with you, and this is the strain gauge. We install it on the reinforcement bar, and it will move with the reinforcement. We weld it at the reinforcement, and by recording the strain in this wire, we can tell the strain in the reinforcement. Seismic instrumentation, these are basically strong motion accelerographs which measure the ground acceleration wherever they installed in all the three directions. Now coming to data acquisition systems, these are the systems which we installed. This is the data logger and this is the channel expansion module. Basically, I can say that this is the heart and this is the extension of that heart, channel expansion module. So we connect the wires of all the instruments here, and this data logger will keep on recording. It has got a chipset in it and a memory card, and pen drive facility also is available, and it can send the data through GSM as well. So it will keep on recording the data which of any instrument which is installed on it, and then it is connected to a web-based software. We have discussed that web-based software as well in the subsequent slides. You see, all these instruments can either be connected to a readout unit for manual reading or a data logger for automatic reading, and subsequently this is connected to the laptop, PC, whatsoever. So by doing so, we so this is the way the data keeps on coming. It keeps on recording at the desired frequency, and it keeps on circulating on our system. But there is a time lag. Okay, if anyone has to analyze this data manually, it will take a lot of time. So there is always a time lag in manual analysis. Then it's expensive because a lot of manpower and a lot of resources will go in doing that analysis using the step sheets, and it's very difficult. Though we can write macros, we have written it, a lot of them, but it's difficult to handle that lot of data, because you were talking of a data, for example, frequency of one data or at one location at one sensor every second for 100 years. So it's a huge amount of data that need to be tackled. So there are chances of human errors, and there is no data available in real time is something which is required. Okay, if we develop a software which is coming, which will analyze the data, then we have very much advantages. We can have the data available in real time. There are not if there are some not working sensors, they can be identified immediately without lot of time, and less manpower is required, and there is less scope of human error, right? We should be able to trigger alarms and on-site visualizations, and data should be able to be generated in real-time reports. I'll show, these are some of the examples where the instrumentation is being carried out in a very nice way. If you want, you can, those who are interested can go in further depth to it. You can write to me and I'll be happy to share more details with you. So this is the because the time is limited, so I'll go a little quickly now. So this is the frequencies which are recommended for monitoring, both during construction, during initial filling dam, and during the operations. Obviously, it will depend on a lot of factors. If at a particular point my my values are coming to be constant, then I can decrease the frequency of monitoring. If the values are values are changing, then it will reduce my frequency of monitoring. So it depends on that. Sorry, increase my frequency of monitoring. So early warning systems, I'll come to early warning system. So in addition to DAP, this is the basically a slide of DAP. So you all know that the slides can be either rotational slide or transitional slide, or there may be block failures. There may be rock falls, there may be over toppling failure, and there may be debris flow. Right? Earth flow, debris flow, creep, there may be a creep failure as well, and lateral spread of the dam sites. What are the geological causes? The geological causes are basically the weak or sensitive materials, weathered materials, shear joints or fissured materials, adversely oriented discontinuity, basically structurally controlled failure, and the contrast in permeability and stiffness of material. And morphological causes may be tectonic or volcanic uplifts, glacial rebounds, which is not very common in most part of our country, right? Neither wave or fluvial and glacial causes are very common, but human causes are very much reasons for the failures, because we are nowadays constructing infrastructure at critical project locations. So this is causing very problems on landslides. You see certain examples which we have seen already of slides. People are facing really challenges to manage with these things. So this is the example of analysis which we do before we decide any instrumentation scheme. Because if we have some values of various engineering parameters, then we need to compare the values with the design values, and until unless we do that, there's no, that values which we are getting from the instrument is meaningless. So I've shared these values we can calculate by doing simple limit state analysis, or by doing numerical analysis, finite element analysis. So we need to do by both, and after doing by both, on then only we need to come to a conclusion of the desired values. So for example, slope failures, critical are displacement, groundwater, direction of movement, magnitude, rate, and depth of failure. So I'll not go into much detail because we have already discussed something about it. So this is, for example, in landslides, what we do is that, tension crack is a very initial indication of a slide to happen. So what we do is that if we see a land tension crank being developed, then we install simply two steel rods, steel pins, which are installed on the either side of the crack, and we put a simple scale or steel ruler to it. And by knowing this deformation, this dimension, we can easily know whether the tension crack is expanding or it's stable. If it is expanding, then it will give us a warning that our structure may fail, and if not, then we should be happy that okay, everything is under control. Similarly, instead of installing this kind of displacement sensor at one cracks, we can combine two or three cracks, and we can uh, put an anchor and a steel wire, tensioned wire, and a measurement scale on the either side. So in this way, it can be automated. Uh, this is the schematic diagram, and this is the photo of site where we have already done this. For example, MPBX, which I have already discussed with you. So how do MPBX help? If we want to know the slip circle location, then if we put different MPBX at different locations, and we know deformations at different levels, so by correlating the deformation of one MPBX to another, to another, to another, and joining a line of deformation at every level, right, we can have an idea of the depth of slip circle and exact location of slip circle, which we have seen in our studies that a slip circle develops. But how to get this slip circle location at site, that actually where it is developing? By installing this MPBX, we can do that. This is the way MPBX. This is this is the way which I was talking. Manually taking the reading of water level. You see, this person is lowering a water level indicator in a pipe, and he will hear the beep. And in not only hear the beep, here a circuit is there. A light will also glow on this instrument. And once the light will turn on, it will indicates that we have reached the water table level. Load cells, I was telling you, that load cell central whole load cells, which is used to monitor the loads in the rock bolts. I'm not sure you are all are familiar with rock bolts or not. Maybe it should have been covered in your curriculum by now. So these rock bolts are basically elements which are used to prevent the landslides. It holds the landslides, it takes the deformation load into it, and it prevents the landslides to happen. So just to check how much load is coming in our load cell, we install this center whole load cells basically. You see, these are the load cells which are installed on this retaining structure or landslide. This is the way it is installed, and it will prevent this from falling. And this is the center hole load cell which is installed. You can see in orange color. These people are installing load cells at various location and site. Now, in addition, we can have surveying techniques. I was telling you that one way is very simple, that you put a plus mark on your structure. But this plus mark is not very visible from very far away, and there are chances of human errors. So for that, what we do is that we install these prisms, which are reflector prisms at different locations on the dam body. This is the hill basically, or where which is we call it rib of the reservoir. Okay, at rib of the reservoir we install a number of instruments, number of prisms, and we go to a point which is presumed to be stable, and we take that point as our benchmark, and we make a concrete pillar in that benchmark, and we install a permanent total station permanently there. This is a robotic total station which is has a program that it will automatically target all the it will automatically keep on targeting all the prisms at desired frequency, and it will keep on recording its x, y, and z coordinates, and the software will help us giving the deformations with respect to time. You see the green, red, and blue fluctuating lines on the right side, right? This is giving me the deformation at every level. You see, we need to protect this instrument from climatic challenges. Hence, we make a small hut type of structure at site, which prevents it. And you see that it will keep on recording data at the desired frequencies, and we will get our desired information every time in the real time. Then we have GNSS sensors as well. So when we move nowadays from our car to any location, in our phone we use that map technology, and we just put the location where we want to go, and that satellites tracks the location of our car and give our location of our car on map, and direct us to the destiny. Similarly, we install the GNSS sensors at various locations, and these locations will connect to a rover, and the rover as well as to satellites. And by knowing the ad, in addition, we install this total station as well, and all the sensors including rovers, they talk to each other. Why? Because if we cannot rely on one technology. If we install total station only, then it will have it the readings will deform. The distance reading will be affected by the distance from the total station from the target, the climatic conditions. If there is dust, then it will have an impact. And if we rely on satellites only, then it will depend on, because at any point of time the sensor should be connected to 8 satellites minimum to get the accuracy levels which we want. And if the weather is not very positive, then there will be the chances that we lose the data. So we don't rely on one system. we integrate all the system. We install total station also, we install GNSS also, and when we correlate the reading of both, then only we confirm what the readings are coming. So the key is in integrating. We integrate all of them. And in addition to all this, we install geotechnical sensors also, which I have discussed till now. We install my MPBX, we install in-place inclinometers, we install pressure cells, we install pore water pressure meters, seepage pressure meters, all of them. And stone motion accelerographs as well. So this is the frequency which we need to act after an earthquake. One is quick check. Immediately after an 1 hour of earthquake, we need to confirm the seismic activity at dam site, which our instrument will give. We need to check the initial assessment of obvious failures. That we need to go through the every part of dam as early as possible. 1 hour is the time which we have set, and we should check that there should not be an sign of failure, right? And if there is, we should have an emergency rescue needs, and we need to notify the authorities accordingly. And the final inspection should be completed in 3 hours time. This is the initial inspection, and second inspection will take within 24 hours, and then we need to act accordingly, and we need to modify our online monitoring systems accordingly. The software which I was talking about, now I'll come to that. So on-site visualization. You see, this is the example of a metro structure, metro line which is being constructed underground. This is from a real-time project which we are handling. And because of this, these all are the buildings, okay? And the real-time software is given as color coding. For example, you see the color which is green is least affected, and the color which is red means that in these structures we have some issues. The deformations are more than what we expected, so we need to act immediately. So this is an example of on-site visualization. Such screens are always in the display of all the major stakeholders: the project manager of the construction site, the general consultant who is the designer of the client, metro authorities. Everyone is able to see this window in real time, and so we can act immediately. In addition, we put this hooter system and this light system at site. So based on the readings, we already put the desired key in the desired limits in our software, and as soon as any sensor exceeds that limit, till the time that sensor is within the values are within the range which we have prescribed in the software, the lights will be green. And as soon as the sensor any particular sensor, these all on the left are the name of and location and IDs of the sensor, crosses that limit, the light will glow red, and this hooter system will give a hooting, and so that the people, the workers, can immediately evacuate the site. So this is what we call as on site visualization system. It is very common for metro projects, not very common for dams, because dams and metros, there is a different in construction philosophies, there is a construction difference in construction timelines, and there is a construction difference in risks associated. Dams are, if you ask me, dams are very designed very over safe, but metros are designed are optimally designed. We don't go that much over safe to overshoot the project cost, and we don't take any risk also. The structure should be safe enough. So the monitoring is very high in metros. So we have sensors, we have nodes, we have gateways, and we have servers. So it's a combination of all of them which give us the desired output. And this is the way we get the readings. You see the vertical ups and downs are the noises, because in any sensor we will, because we are converting the analog data to digital data, and while we convert analog to digital, there will be noises because of other factors, right? If there is a magnetic field, there will be a noise. So we need to filter that noise. This filtration can be done manually, or this filtration nowadays is being done by software also. And after filtration, the original data is on the left hand side. After the noise cancellation, we will have the data as smooth as you see on the right hand side, which shows the variation with time. So immediate, this is what I've been talking. for data processing and evaluation systems. Okay, so it's a comparison about manual readings and real-time monitoring networks. So you can read the advantages and disadvantages, but the basic first idea I have already shared with you. Collection methods may be manual and automated collection, manual collection, visual inspection, and real-time screening. I've discussed all of them with you. Data presentation is very critical. As I showed you, if you present a data, if my presentation should be as good that there should not be a need of manually reading any value. Like I showed you, if the buildings here, no, you see here, by this presentation only I should be able to know, okay, I need to put attention on the buildings which are red, rather than reading data and then coming to that conclusion. So data presentation makes a very big role in taking decision. It's a very big tool of taking decision. So this is also one of the project where we have installed a number of instruments. This is how the data is coming: initial data and noise filtered data, right? This is the initial data and noise filtered data. We basically set three values: level 1, level 2, and level 3. The level 1, for example, is for example, let us say that my design value is 100 microstrain at any point. It is expected by my design that the deformation at the point are going to be of the level of 100 microstrains. So I in my software I'll feed three values. I'll feed 50 microstrain, 70 microstrain, and 90 microstrain. So if it is 50 microstrain, I'm fine. Less than 50 microstrain, I'm fine. If it approaches 70 microscales, then I need to just recheck all the things manually, that what is happening, why it's going so close, because our design has got so much factor of safeties. It has got material factor of safety, it has got load factor of safety of 1.5. For example, concrete, we design it only to the level of 0.42 fck, but really it has capacity of fck. So it should not reach even 70% of design values. But if it reach 90% of design values, then we should immediately act. So normally we divide all the engineering parameters into three levels: level 50, level 70, and level 90. So temperature compensation is very big factor, because I've told you all the sensors which are measuring the data rely on the length of the wire, and the length of the wire may get changed because of two reasons. One is the load which is coming, which will cause the length of wire to change, which we actually want to monitor. And another is the temperature effect. The length will be changed because of temperature also, which we don't want to monitor. So we need to record at every sensor location the temperature at that sensor also location as well, so that we can do the temperature compensation, and we can reduce the reading length of wire, which is change in length of wire which is caused due to temperature change. Then only we will come to know the exact length of change. So I discussed you alert level, action level, alarm level. There were three levels. This is 50, 70, and 90 level. I think we have got only 10-15 minutes. So I'll quickly, because I've discussed most of the things already. So quality control and checklist, we should calibrate all the instruments. We should verify that the data coming is right. Then we should validate them. And then we should confirm the accuracy, and we should do a regular inspection. Okay. So there are certain limitations also of instrumentation scheme. Okay, it collects only the assigned information. It measures the limit to the installed locations. सुभाष मैं मीटिंग में हूँ यार, खत्म होगी तो बात करूंगा. Okay, for example, if the dam body is 150 meters, okay, I cannot install instrument at every meter. So if I choose only two sections, so I'm getting the level or the engineering values of only those two sections, and with the assumption that ground is behaving homogeneously. But in case heterogeneously is more, then I need to choose more sections. Then only I'll be able to get the correct values. it cannot capture the behavior between the measurement points, which I have clearly discussed with you. There is a mortality rate of sensors are very high, because these sensors are installed at inside the structure, and it goes to it has to overcome various factors, like at time of construction there may be some damages. During this there is high chances that during the construction the instrument wires may go cut and things like that. So sensors failures and malfunctions, which is a very high possibility. And environmental effect may affect the accuracy. For example, I was talking about the readings of a total station which we are taking at from the prism. It will depend on the environment factors. Okay, so what we need to do is that we need to have the comprehensive planning. We need to carefully instrument the sections and placements. We need to choose very carefully. We need, for example, we need to understand wherever my structure properties are changing, and at every structure properties we should choose a sensor. We should have some redundancy. As I told you that the sensors have high mortality rate, so we should have redundancy, and we should always not only depend on mechanical electronic reading. We should have some sensors which take manual reading also. For example, because of any reason whatsoever, the power goes off of that structure, electronics instruments are not going to work, but at that time manual instruments will still work. So we should always have a optimum combination of manual readings and electronics readings, right? And professional interpretation is very essential, because if you will stand in near to a very close to a load cell, or my construction vehicle will go very near to a load cell, it will give me a false alarm. It will give me high pressure, which is not because of structure but because of the reason that a construction vehicle was very close to it at that point of time. So there needs to, here comes the professional interpretation skills, which are very critical. Visual inspection plays a very big role. If my instrument is showing a dam deformation of, for example, 20 meters, and visually I don't feel it's even 1 meter, it makes a difference. Then I need to go and check what's going wrong. So regular site visits are very much critical, and so on. Some of the incidences, unfortunate incidences like morbid tragedy, uh, these instrumentations play a very big role in preventing that. So I think uh, field monitoring challenges I've already discussed with you. Okay, the challenges are that most of the time we don't know what to monitor, where to monitor, how the structure will behave. We don't have numerical modeling results. The deformations are very large and pressures are very high. These instruments are installed in corrosive environment. These are subjected to various temperature fluctuations. There are shock due to blasting construction activities. There is a vandalism due to construction activities, and power supplies and lighting also affect the instruments. Hence the mortality rate of instrument is very high. I must say that out of the 100 instruments installed, 40 are, there are very high chances that 40 will go bad and only 60 will work. So this is the practical challenge which we need to live with. So action plan is that we should repair and rectify as soon as we know that some instrument is behaving abruptly. Uh, if the instrument embedded reinforcements, if the embedded instruments it cannot be repaired, then we must formally abandon that instrument and we must install another instrument. Essential observations are reservoir water levels, hydrometeorological data, sewage monitoring, displacement, and uplift pressure. These are absolutely essential, and here we should always install some mechanical instruments. Thank you, and I leave some time for questions, whatever you want to ask.
Thank you so much, sir. Now the forum is open for Q&A session. If you have any queries, you can type in the chat. We already have some question asked that I will read and sir will
Yeah,
answer.
yeah, ma'am. If you can read, I'll try to answer them as I told initially.
Okay. So the first question is, if the dams are impervious, Why do we design flow nets, flow lines, filters on the downstream, toe drains, phreatic lines, and cutoffs? Do they not become redundant
Redundant.
if the dam structure was to be impervious? How can these monitoring instruments be incorporated in the already existing structures?
Yeah, I'll like to answer this question. Very good question. First of all, let me tell you, no material in this world is impervious. Okay, we are talking of a structure which with a design life of 100 years. And in civil engineering, you might have done some permeability test on soils, permeability test on rock, permeability test on concrete as well. The permeability of soil, the most impervious soil, the very low permeable soil is having a permeability of 10 is to power, for example, 10 is to power minus 8 meters per second, right? Hello, am I
Yes,
audible?
yes, sir. Yes, sir. You are audible.
Okay, so if you do a quick calculation, okay, just let me share my screen.
So also it is being asked in the context of Bhakra Nangal Dam.
Bhagra Nangal Dam, very good.
Bhakra Nangal Dam.
If any one of you get a chance to come in the gallery, you know the dam galleries. In dam, we make some galleries. Why? Because we should be able to go in different part of dam. Bhagranamal Dam is a huge dam, right? It's around 200-meter high dam, and say, for example, 200-meter high, base width is say 800 meters, and length is at 150 meters. So that big a concrete structure will have some galleries at different location, so that we can go and move into those galleries and inspect the various part of the dams. So I have been to the galleries. I'm not sure whether you'll get a chance to go or not, but if in case you get a chance to go, when you go in that dam, you see the dam, how water is coming in that dam. There's a huge water is coming in that dam galleries. Why? Because concrete is also not impermeable. So if you do a quick calculation, I'll try to do it for you if it is there. So 1 upon 1. Okay, so this is the this much meter per second is the permeability of very impervious soil. Okay, so I have to design that for 100 years, right? So is equal to 100 years into 365 days into 24 hours into 60 minutes into 60 seconds. Okay, and how much will be the movement of water? So the water is going to move 31 meters. If the dam is that much consistent, if the permeability is this one, and this is very very low permeability. So my friend, no dam is impervious. Only thing is that if we have two type of dams, concrete dams has got very relatively is relatively highly impervious, and earth dams are relatively less impervious. The core is impervious, right? Although, but still the dam is impervious. Point number one. Point number two, the water not doesn't necessarily flow from the body of dam. It flows from the foundation of the dam as well. That is why I've shown you that we provide curtains. You see, I'll just go to that. Just a minute. You see, these are grout curtains. We put grout curtains below the dam because water is not only moving this way, water is moving this way as well. So the answer to your question is that first, every dam is pervious. Only thing is that the level of impermeability which we can attain. Point number one, and hence it is very much required to put the drainage galleries and riprap structures and other things which can collect the seepage water. If I am able to answer your question. And what was the other part of your question?
Sir, the second part of the question was like we already have the existing infrastructures which have been
Yeah,
existing over a period of last almost 75 odd years.
yeah, yeah.
Now, point is all these, in fact, the monitoring, in fact, techniques or tools which have come into the market So how can we integrate with the existing structures? I'm not talking of only of the dam only. I'm just
Yeah.
or relating it with reference to the old constructions, old building which are existing. There are some
Yeah.
heritage
Yeah.
buildings which are there.
Very right. Very right.
So that's
So
how we look at it.
if there are two
And the
things,
second part, sir, firstly, in the dam issue, sir, there is definitely there is some amount of seepage which is allowed through the dam.
yeah,
I remember correctly when we used to read the infra design of the dams, high
yeah,
dams. So there is a freeboard, and thereafter there is a flow line from where, in fact, sir, exactly there is a profiling which is made, and based on that profiling, then your spillways and other infra issues are designed, and then you allow the water to seep through the flow line, and it actually should not be crossing the filter. It has to be emanating, or it has to be culminating in the filter, so that any particulate matter which may come along with the flow, it gets all entrapped there. So
yeah,
that
you're
was
right.
the context, and the further to it, so now, like, in fact, recently we had floods,
Yeah,
and the floods were so severe that the phreatic line, the saturation line had risen up.
yeah,
Whereas for stability of the dam, sir, you require to have the phreatic line in fact as low as possible.
very right.
So therein the issue came about the seepage, and how in fact can be what can be done to ensure, like, in fact, couldn't this in fact flood situation be predicted beforehand? Why in fact the things were allowed to reach that level, that the water, the or phreatic line or the saturation line, it had risen all the way up to the top of the dam. I think it was already, in fact, had the water crossed over the dam, the structural stability of the dam, it was endangered actually, sir.
Okay, so I'll take up all the points one by one. First of all, there is this line which we draw, flow net, we draw the phreatic line inside the dam. I'm taking, I'm not talking the open surface or inside any structure for that matter.
Yes, yes, dam, sir.
These all are the things which exist only in paper. Okay, in if you talk about the real situation, yes, broadly it follows, but at minute levels it doesn't follow that smooth line. Okay, it's not a line which will govern that my water has to be below that and it will go below that. There is no impervious line there in the field. It depends on many factors. It depends on the relative permeability. Water is free to move and it will take the path of least resistance. If I for example in my dam, if you can see my cursor, I'm just talking a hypothetical situation, my friend. If I make a dam, you can see my cursor movement or
Yes,
no?
yes, yes,
Okay,
yes.
a hypothetical situation. If I make my core like this, okay,
Mm-hmm.
है ना, अगर मैं कोर को ऐसा बना दूं, if I make my core like this and water at this is having a head of 200 meters, then the water will start moving like this. You agree?
Mm-hmm.
So the phreatic line or the flow net are being defined by the movement of water. It's other way around, and it's not the flow lines which are directing the movement of water. Water is always taking the path which is least permeable path. And if the things at site are as which I designed, which I thought it will be, this is completely homogeneous isotropic material. Okay, there's a concept of chili and dyne. We design it as considering chili. Chili means our system is continuous, our system is homogeneous, our system is isotropic, okay, our system is linear elastic, and our behaves linear statistically. This is chili. When you will come in practical life, you will understand these things. But actually, no structure is chili. Actually, the structures are dyne. Our structure is discontinuous, our structure is non-homogeneous, our structure is non-linear, and it's non-isotropic. So the behavior, that is the way where we need to actually this is more specific in case when we are handling rock and concrete, rock and soil. Okay, concrete is relatively better, steel is much better. Why? Because steel is produced in factory, it is produced in factory controlled conditions. Concrete is produced at site, it is produced at site controlled conditions, but still it's a man-made material. You can have certain level of desired parameters into it, but earth, concrete, rock, earth and rock are not man-made material. They are completely dynamic behavior. So all that which you will study in your life till your even PhD, once you will go to field and you will actually design the structure, then you have to design it based on dyne. You have to model it as a discontinuum material. You have to model it as a linearly non-isotropic material, and you have to actually observe the behavior. And hence, in the observational method and risk methods are nowadays very common in geotech engineering, in rock engineering, but not in concrete and not in steel, because we don't need to worry about that there. Okay.
Yes.
So this
Earlier,
is one.
sir,
Yeah,
I
yeah.
think earlier, I think the flow line or these were the parameters which actually used to be
You are
seen.
right. You are right. So I'm telling you the practical things, my friend.
Sir,
Okay.
sorry to interrupt. Just a
Yeah.
quick reminder that
Sure.
we need to wind this up in 5-10 minutes. So
Okay. So I think let us take the next question, my friend. You can interact with me and otherwise
Surely
also. So
enough, sir. I
I'll
think
be
it is a
happy.
very, very, very interactive, very good session, sir. And I really, in fact, loved, in fact, interacting with you on this.
Very, very right. No
Yes.
problem. I'll request madam to share my email address with
Surely
you
enough, sir.
guys so that you
Thank
can.
you so much.
And
Thank you.
another question, ma'am. Another question which I can take up
So
in
the
that
next
time.
question is from Dr. Yuvraj.
Yeah,
Is there
doctor.
any caudal provision available to calculate slope stability?
Yes, definitely. There is Indian codes available to design the slopes. There are ESTM codes. There are many codes. Military Corps of Engineers from America has given a very nice guidelines. So yes, your answer is right. There are codal provisions available for the design of slopes in India as well as outside India.
Thank you, sir. So we have the last question from Akash Pravapanda.
Yeah,
In
Akash.
important infrastructures like dam, if some of these sensors stop working, how it will affect the monitoring process and what is usually done in this type of situations?
Yeah, very good question. I'll tell you, not some, as I told that, say if these all are the instruments installed, I'll take this example. I'm sure that 40% will stop working, because I told you that the instruments have got very high mortality rate. This is the truth which we need to live with, because we don't need the data for 1 year. We need the data for 100 years, right? So now coming back to the instrument, this answer will answer one of the question which my friend asked, that what about the existing structures. Now the instruments which are installed at the surface, it's very easy to replace them. Okay. The instruments which are installed inside, once they have gone damaged, it's very difficult to repair them. Sorry. Surface instruments can be repaired. The instruments which are installed inside cannot be repaired. The only thing is that you live with the remaining instruments data and be happy about it, which normally we do. Another thing is you drill a fresh borehole and you install the instrument once again, but that will never give you the in situ site condition, the institute side data, because it will be a disturbed value, not an undisturbed value. Second, by drilling a hole inside a stable structure will I'm saying may. If you ask me personally, I'm least bothered. I'm confident it will not, but many people are of the belief that it may impart the safety of dam, so they will not allow you to do it, the government agencies. So that is why the answer is that initially only you install one instead of installing 100 instruments. If 100 are required, you install 160 instrument with the belief that 40 to 60 will die, and I'll have to live with 100 instruments only. Hello.
Yes, sir.
Thank you, sir. That concludes today's session. Thank you, Mr. Heman Manchanda, sir, for that highly
Thank you, ma'am.
specialized and practical session on structural health monitoring and instrumentation. Your experience and insight has definitely enriched our minds and has added value to our session, to our program.
Thank you, ma'am,
With
and
this,
thanks everyone for listening to me. Because visualizing these things and listening to instrumentation for the field guys is relatively a welcome subject, because they actually understand. I'm sure many of you, these many of the terms will be very new, and it would have been difficult to digest. But if you have any questions, you can ask. I'll be happy to answer.
Kanya,
Yeah.
can we have one group photograph? Heman sir, can we
yes, sir,
have one
yes.
group photograph so that for our records we can open our
So,
cameras?
participants have successfully completed day 4 of the FTP I now request everyone to open their camera so we can take a group photo.
You didn't told me in the beginning, huh? So please don't mind. Is my camera working?
Yes, sir.
I'm not sure how, how the photo will come, but fine. No, it doesn't matter.
Coming.
Kanya, have we taken
Yes, sir.
the photograph?
Yes, sir.
Yes, sir.
Okay,
Thank
thank you,
you.
Heman, sir.
Thank you, sir. Thanks a lot.
Thank
Thank you,
you.
everyone.
Thank you all. Just a final and critical reminder before we wind up today's session. Please ensure that you have filled both the form for the attendance in the chat window. Also, we eagerly anticipate seeing you all back online tomorrow, Friday, 14th November 2025 for day 5 of the FTP. Good night and thank you all for joining.
Thank you. Thank you, everyone. Thank you, ma'am. Thank you, sir. Thank you.
Thank
Bye-bye.
you, sir.
Take care.